I'm going to start the recording. Welcome, everybody. Today is the 1st of February in Dallas, or later in earlier time zones around the globe. We're just anticipating a giant northern to come through and freeze us all. So Pat will be with you in spirit, and Chris, just another day or so. We're going to go from about 70 today to about 19 Fahrenheit in less than like 12 hours, I think. So that'll be exciting. Brief housekeeping update. Nothing much changed since last week. There's a good Discord server, so ping one of us if you want an invitation link. Our annual meeting is still in hold as we don't have people volunteering to run just yet. So I'm continuing to just kind of quietly serve as acting president, I suppose. But we do have Jack scheduled for the 19th of February. So it'll be the third Saturday, not the second, but Jack is going to give us a presentation, and that'll be fantastic. And then we have a handful of other items in queue with people more or less penciled in. So if somebody wants to step up and help run the club, we got a good start for you already. And with that in mind, we have on deck, for those that have joined in the last few minutes before the recording started, Iron Rain's going to give update on their competition robot. And then we have updates from roughly in this order, Chris, Pat, Ray, myself, Carl, and then Paul, and then a free-for-all. So we've got a good queue online for tonight. Who knows where our conversation will take us, but to lead us off, it looks like it's time for Iron Rain to present their amazing expandable robot.
Yes, thank you. Obviously this is maybe going to be just a bit more hands-on because we're doing some wiring remanagement and a little bit of upkeep on the gripper up there.
Yeah.
Fixing a stripped gear or two. But basically, the original concept that we had gone for hasn't much changed, where we've got a pair of differential wheels up here, and then we have a swerve wheel in the back here. These are all similar modules where you've got just two plates sandwiching a large wheel. We need this large wheel to get over these boundaries. And we're also using the large wheel because odometry isn't the most important in this year's game, except for in the first little bit part of it, which is the auton section, and the error that will accumulate over that 30-second auton section is not going to be too great, or at least it's not going to be any more than if we were using any other setup. Then we've got a arm here that is made out of CNC carbon fiber. It's being driven by two digital servos, and that just gives us a little bit more control over it. We went with servos instead of real motors with encoders, servo motors, just because of the weight constraints. This has to move really fast. And I'll get into why in a little bit, but basically it has to move really fast, and so it has to be super light. So carbon fiber is the material of choice, and we can just kind of assume that the arm's going to be where it is. It's not going to be encountering any big forces, or at least it shouldn't be. So we can assume the arm is where it is after a certain amount of time.
Yeah. So that's a little bit about our robot. I believe last time we saw it, we hadn't really driven the robot that much. And between now and then, we've gotten a lot of drive practice. Or not really a lot, but relatively a lot.
We've gotten more drive practice.
And there were some issues that we ran into, and you'll see some additions to our robot. So over here, we have these like training wheels.
We call them Outriggers.
Yeah, we call them Outriggers, I guess, because the name training wheel is...
Yeah, it's got a little bit of a
negative
connotation.
You know, because we totally know how to drive this thing, right? So we've created these Outriggers, which should hopefully stabilize the back of the robot a little bit. because we were running with into a lot of issues with tipping over, especially when we were getting over these barriers, which these wheels were designed to handle. And looking at this wheel, you'll notice it's a little bit flat. I'm not sure how well you can see that on camera, but it's very flat. So we've designed our own wheels that we're going to 3D print out of NinjaFlex and nylon. So right here's, this print failed early, but you can see our design for the wheel. We have a nylon hub and a NinjaFlex tread. This NinjaFlex isn't rigid enough, so we're gonna have to make some changes to our printing profile to give it a little bit of strength and improve the quality a little bit. You can see we printed it at a pretty.
We should say that's not particularly our design. It's heavily inspired by a rover, right?
Oh yes, okay. I guess it was one of the NASA rovers.
Yeah.
Yeah, so it was inspired by one of the NASA rovers. But yeah, so this print failed, so we had to cut it short a little bit. So yeah, that's how we're gonna solve that problem. Another change that you'll notice, I'm gonna pull this robot forward a little bit. Wheel doesn't come apart. We changed the claw, so you can see it's kind of dragging itself along here. So we created this carbon fiber claw, which we're having some problems with. So how this works is we have a servo just turning these grippers, and they're connected to each other through a series of these little plastic gears. But when we like run into a wall or some sort of obstacle on the field, these gears undergo a lot of stress because they're out in the front. So they tend to strip a lot, and that's something that we're struggling to deal with right now. We think we may want to try using some metal gears, but a short-term solution would be just programming the robot to keep the claw up while it's moving and not picking up an element. So kind of want to hear your thoughts on that, if you have any ideas about how we could kind of mitigate the gear stripping. And when the gears strip, the claw can't close all the way and can't properly grip one of the field elements, so we can't score.
And actually, speaking of which, I'd like to talk really briefly about what the purpose of the game is. So you can think of our field as just a big square. We start out in one of the corners, and the main objective is that there are these depots, you can call them, where they stack a bunch of elements.
It's that white square in the back.
Yeah, and you have to go and grab each element one by one. You can't carry more than one element, or else it's a game penalty. And then you have to put it on that red thing over there. It's not supposed to be over there. It's supposed to be, yeah, like somewhere over here. But you can see that in a little bit more quality now. And that's that might explain a little bit more why this is the way it is. So the cycle is you get into the shipping hub, or you get into the warehouse with all the field elements. You grab it, you grab it, and the robot's going to be short so that it can be within the warehouse entirely. Has to be within the warehouse entirely to actually pick up the field element, or else that's a penalty. Then we can drive straight back out by extending that swerve, and then we can deposit that element that is transferred. Basically, this gripper goes all the way up and into the bucket. We demo that, but again.
Yeah, so yeah, you can see that the gripper is kind of many pieces. But yes, it'll hand off. The gripper will hand off into the bucket. The bucket will turn around and dump it into one of these three levels. The higher the level, the more points you get for each element.
Yeah.
We've developed this transfer system a lot more since the last time we saw you guys. But one thing we've been currently trying to implement is that we're trying to create a sensor right on the arm. And so when it's actually filtering elements, there's 3 different kinds of elements. Four different kinds really, but here's what they mainly look like. You've got the white ball, right? The silver freight.
Like I think it's called a wiffle ball, something like that.
Yeah, wiffle ball. Sounds accurate. And then those 3 are all cubes, but each of them have different kinds of weights on them. And so scoring a particular cube with more weights in it gives us a lot more points. And so what we want to do during our autonomous period is every robotics team's, I guess, big ambition to create a completely autonomous robot. And our way of getting closer to the step is with this arm. And so this sensor basically helps ensure that we don't have to worry about the task of filtering the right elements. but the arm basically carries that task out for us. And so then transferring things from like this bucket system over here to the gripper, which is currently still under construction, would be a lot more simplified. And also, we're looking for names for the arm, some snazzy names to present to our competition judges next Saturday. So if you guys have any suggestions, that would be appreciated.
I think the arm works fine.
Right.
I guess
A
some
little
people
bit
want
simplistic.
a more creative name for it. I think the arm is very descriptive.
Yeah. One note about the arm that is kind of big to its use is that how the field geometry is. It is kind of most effective for the arm to be going from this transfer position all the way out, pretty much straight back to where the thing that you're putting the element in is. So this arm actually traverses through itself. I'm not on the camera anymore, so I can't move it. But it traverses through itself so that we can actually get a full range there, and we can get between those two positions rather quickly.
Obviously, it's more accurate when the robot's doing it than when I'm doing it. There you go. That's better.
Yeah. The final little bit of our robot is this mechanism right here. It's really rather simple, though we're kind of proud, I suppose, of the launch mechanism that we've come up with for it.
It's really genius. It's genius.
So you can see right now that it's, how it is. It's not really deployed.
Yeah, so we have to keep our robot within an 18 by 18 by 18 cube. But part of the game is to spin a little disc on the corner of the field. And so in order to reach that far out, we have to have some way to deploy this little like spinner wheel. So we use this rubber band to keep it held back. But on the robot startup, the robot will spin the wheel, and then the rubber band will release once it gets past a certain point. Oh, well, it's not held in. Okay.
Yeah, we don't have the rubber band quite attached because this is a newer part. We just finished developing a new version of it. You can see it's now 2 carbon fiber sheets, which is more professional. We're also looking at modifying it further. That's another reason why it's not on, because we need a way to quickly switch between the 2 sides here for compatibility with different starting positions in the autonomous section. So,
So it has to be hot swappable. I guess the last thing we really want to point out that's a major change from our last version, or the last time you saw it, is on the gripper we do have a color/distance sensor, which goes with what she was talking about, how we want to make the robot operate on its own as much as possible with the least driver input. So when we approach an element, whether it be a cube or one of the balls, it automatically picks it up and transfers it into the bucket so we can score it into one of the shipping hubs.
yeah.
And then one last thing that we wanted y'all's input with, sorry, camera on goes pretty bad, but we've been trying to calculate the exact center of mass of the robot. So as we mentioned earlier, the point of these outriggers or these training wheels is to ensure that when the robot tips over, we have something to keep it supported. But we plan to eliminate this completely by making sure the robot has no possible way of tipping over. But that means finding a center of mass. So if you look down back at the robot over here, you'll notice that it can extend back and forth. It's not in that position right now. But when it does, its center of mass varies a little bit, especially when that arm extends out or when it swivels from side to side. And so we're trying to create a function to represent the center of mass, which would help us make it a lot more easier to eliminate any possibility of the robot tipping over.
We can limit like motor powers in code to make sure that it doesn't like the kinematics of the whole thing doesn't like stop real quick or to tip over.
Right, but we're looking for is a, I guess, more permanent solution, which is why we're trying to find the center of mass.
I think the outriggers are permanent.
Yeah.
So if you guys have any suggestions as to how we can start to work on those calculations, that would be appreciated.
I know we've said final like 3 or 4 times now, so I'm gonna say another one. Kind of our future plans with this robot in terms of code, kind of coming off of that. We'd love to get this whole thing in like a proper like 3D based kinematic model, and then also including like the center of mass calculations and all that. We'd like to, be able to do general kinematics on it. The arm right now, it's not. It's being driven by forward kinematics, but because of how we have it all set up, we've got different positions that the driver just needs to press a single button to get to, which reduces the amount of button presses that the driver has to do. So in the future, we'd like to do inverse kinematics on the arm, though understandably, it'd be really difficult to do that with the servos that don't have feedback on the encoders. We would do servos with encoder feedback, but it's not allowed in the current rule set. We could put an encoder on the arm, but then we'd have to, well, it'd just be more wires, quite honestly. And we're still trying to keep the weight of that arm down. And then I guess, and on the code side of things, if you all know any 3D based inverse kinematics libraries for Java, like the only thing that we were able to find ever was Calico, but the documentation on that it's all right, and it doesn't include a translation joint between these two. Like, we'd like to do inverse kinematics on the arm and then treat the entire swivel like stack as its own thing, so that we can position it on the field however we like. We just give it an end effector, which is like thank you. Just we'd put like the end effector to be like the scoring hub, and the robot would just do its thing. So if y'all know of any libraries in Java for that, that'd be wonderful. Because the only other option would be like Unity.
And that concludes our initial presentation, and we're open for questions.
Yeah.
And advice.
Advice, yes.
Yeah.
Mostly advice.
Nice.
Hey, I have a question. Large cranes use a counterbalance to keep the crane upright, because if you have too much load, pulls it over. But if you can move a counterbalance back and forth, you can keep the crane upright, which is really good, because when they fall, they tend to damage a lot of things. Have you guys thought about that?
No.
Like a
Actually,
counterbalance to move?
that's a good suggestion, totally. And the kinematics on that wouldn't, or the figuring out like what angle the weight needs to be would be all that difficult, I don't think.
Yeah, if you deviate a little off, horizontal, that which way the weight has to go, because and you could move it fairly quickly, because I'm assuming your arm is going to move fairly quickly, and
Yeah.
so, but
What's the ratio, though? It sounds like you got a wiffle ball, which I think of as being pretty light, to some yellow cubes that have like one yellow cube will have the most weight, and then there will be ones in between. So, like, what's the ratio in mass of the different objects you have to lift?
Oh, we also have to lift these dots. We didn't mention that earlier.
Those are pretty low.
Okay.
Yeah, that's really it.
So I don't actually know the weight of these off the top of my head, but if I could guess, this is probably a couple, 3-4 times heavier than the wiffle ball.
3 or 4 times.
Yeah. Okay. So this cube is made of plastic, and it has 4 little weights. This is the heaviest object that we're gonna have to move. And I would say it's probably 4 or 5 times heavier than the ball.
Fish story keeps getting bigger.
Because the counterbalance plan, then, because of the different loads of the objects, the counterbalance, if you wanted to be precise about it, might need to take that into effect, right?
Oh, good point.
Yeah.
oh yeah, definitely would.
And
But I think
dynamically, because
if you could get the counterbalance to move, like in a servo mechanism, you could probably keep it balanced fairly well. Because
Yeah.
as soon as you start to tip in one direction, you need to push the weight out a little bit more to compensate, and you'll might even be able to make it closed loop. That would be funky.
and then Ray, think about it though, Ray. As soon as you start to slew these weights around, now you have inertia to worry about.
Yeah.
Yeah, so the issue, so the robot could theoretically know whether it had a ball or a cube based on the color, but it would be hard to figure out the weight of the cube if we did pick up the cube, unless we were like looking at voltage or something
Well,
whenever we lifted it up.
We can't
Yeah.
look at voltage because they're servos. So
Oh.
the SDK doesn't support that.
There you go.
Also be amperage. So
Oh,
yeah.
I don't know. I just work here.
we could implement a force sensor, though I don't know how accurate that would be because we're going to be literally just like chucking these things in there and immediately just like flinging around the arm.
So the idea is to move these the shortest distance as possible, which is why the robot extends, so we don't actually have to drive around.
No. On the the counterbalance, what we could do, well, shoot, the other problem with the counterbalance is that since this is self-intersecting, since the arm is self-intersecting, there isn't much of a we could do if it wasn't self-intersecting, we could do a coaxial or like a what is it coaxial? What have we been doing in the previous arms? It's like coaxial, so we'd have like 2 outputs on it. We've done that in the past for several of our different arms, but there wouldn't be too much space for a weight flinging around there.
Does the robot have an IMU?
We have several, yes.
So you do know when it's tipping.
Yeah,
And you
there
could,
are. Oh, sorry.
so you could build a closed loop around that.
Yes. The issue with that is that our drive method is still in development. It needs a little bit more work to be smooth because right now it's really jerky. So in the process of driving around normally, it tips about just a little bit. We don't have perfect IMU readouts on this back section here. Obviously, once it's extended, there's going to be a little bit of twist, which is fine. It's not enough for the robot to not function, but in theory, yeah, we could totally grab the IMU data off of that that hub right there. Actually, you can't see that at all. That hub right there, that's kind of vertical. There is an IMU in there, and then there's going to be an IMU on this front section here. It's going to be mounted to the base. That is something we can certainly look into, but I don't know if I just don't know how we'd filter out those nominal.
That's kind of a standard robotics problem. An example might be that I've seen using the amount of current draw to determine whether or not you've collided with something. And the problem in that case is that there are spikes in the current draw when you're just normally driving around. So you have to differentiate those spikes from real collisions. That's basically what you're saying, that in normal driving around, there would be some tipping, and you have to differentiate that from the tipping that's dangerous. That can be done by looking at it in time, that is, how long does it last, or how high is the spike. Maybe you don't respond to high spikes that are short, but that you'd have to determine that empirically. But basically, that's just kind of the noisy data problem, right?
Yeah. We've worked with noisy data. It's not our specialty. We can certainly look into it.
What about? I'm thinking of some of these 2-wheel, like bicycle style robots, or even the unicycle style robots, and they use a flywheel and angular momentum to help maintain balance. So it gives it some stability just because it's mass spinning around. But then because of the right-hand rule, when you change the velocity of the spin, it induces more torque one way or another. And I know that that's one of the ways that that they've stabilized those kinds of robots with 2 wheels. I don't know what it would take for a robot that size. Either a lightweight spinning super fast or a heavier weight spinning a little faster, not so fast. But
I don't know if you maybe remember our last year's robot. I don't know if.
Yeah, the disc, the
Yeah.
Yeah, have a circle.
I think we were running up to just about the limit on kinetic energy that we could have in our robot, like stored. There's a rule on that, and also
Really?
the output of the battery was a big issue on that one. Then again, that was like super high RPM, so I don't know if adding weight is our solution though.
Yeah,
Plus-
that's the only downside of that approach. I mean, and the mask gives, I think it's a second order low pass filter or something like it, or first order low pass filter. But
But that type of like gyroscope requires also like super high precision machining, right? So it doesn't get off balance. So
Yeah,
and
it's a
that's
little-
not necessarily something we're really known for.
Last year, our flywheel, we literally we took stock into a shop and we like talked to the guy for like probably a month and nothing ever came of it. We never got around to actually machining a proper flywheel last year. Year that it was so critical.
And you could just hear it. It was just rattling the whole time. So our little CNC probably isn't cut for making something like that.
Yeah.
I would also just observe that even if you're not allowed to have encoders on your servos, that the command, the control sent to the servo is a pretty good proxy of its position as long as the servo's not overloaded. I have a camera mount that I calculate its offsets that way. And as I say, depending on what the load is, the command that you're sending it is a pretty good proxy for its angle. And even if it's not as precise as an encoder would be, it's quite useful. You guys might look at that.
Oh, certainly. Actually, how we have it is we've got a normalized conversion rate to we can basically just tell the servos to go to an angle. We pass that through a function to give it the PWM output that it requires. So we kind of do operate on the basis of rough angle. You know, we tell it to go there, we assume it gets there.
So you're already doing that.
Somewhat, yes, but it is. I do appreciate the suggestion.
I guess that's the assumption with any RC servo, right? You give it a command, and you just didn't give it a command to give it a command. You want it to go to some angle or something. So
Yeah, but the way that stuff was developed was for flying radio controlled airplanes.
we had human in the loop.
Yeah, you got a human in the loop. If you didn't get enough angle, you give it more stick, you know.
Whatever it
oh
needs.
yeah. But
If you
yeah,
slew
well,
your,
I think we're just saying the assumption that whatever command you give a servo to, it's open loop. You're assuming it got there, right?
You're saying because of the definition of what a servo is.
Yes.
It gets close enough, you know.
Yeah.
It'll get in the area.
It's really fine for its application.
Yeah, some servos have access to their potentiometer too, so you can close the loop.
Yeah. So
That's,
those are the ones that are not allowed. We were looking into those.
How are your outriggers working? Have you actually tried to drive over those things, over those pipes or whatever they are fast?
No, we haven't. Sorry, go on.
Yeah.
Well,
So,
the reason why I'm saying is usually with a caster, which I think you could assume they're casters, usually the maximum height they can pull over is about half the wheel height or the radius. That's another way of thinking of it. So those wheels, those Omni Wheels, I guess they are the Omni Wheels.
yes, they're
They look like they might actually, if you really move quickly, they might snag that obstacle and give you a real problem.
so
So one of the thoughts I had is instead of your outriggers, you could double up your tire on the front. So you have two tires in the front that are, say, maybe ½ inch apart. And that would give you a wider footprint, and also so you get some stability out of it. And you probably find that you could drive over that without the outriggers. So,
Ooh.
I mean, that's an idea.
So theoretically, it would be a ton. Well, it would be a lot more stable if we had four wheels.
Well,
We-
yeah, but I'm just saying on the the front wheels, you can still treat them the way you're treating them now. They're closer together, so they're not as wide out. They're not four wheels. You know what I'm saying? They're
Yeah.
two wheels next to each other.
Yeah, I get that. And
Okay.
because we're custom manufacturing our next wheels, we could even just make this wheel wider. So that would solve that problem too, I think. But the way that these outriggers were designed is that they would be off the ground high enough so that if we were just going over these barriers, they could just graze over. But what we didn't account for was how this wheel was basically flat. So they're on the ground now, and if we went over these barriers at speed, it would probably do not good things to the robot.
You know,
So to answer your
Break it off.
question,
because you see the way you got it now, you're gonna figure going over those pipes. I don't know what they are. They look like pipes to me.
There.
PVC?
Okay, when you hit them, right now you've got essentially two prongs, if you want to think of them.
Mhm.
And if they don't hit it square, they're going to hit it square. You know what I'm saying? They're gonna jerk the robot to where they both hit. And there's also going to be a moment from the center pivot of your front, what do you want to call it, caster to that Omni wheel. So there's going to be a lot of force there on them, and I'm afraid that they're not going to have equal force on them when they're put into play. And so it's going to cause your robot to rack. And since it's got this big sliding element, it probably shouldn't rack.
Yeah.
So I mean that's something that I would like I say I would consider opening up your yoke or just printing a bigger wheel, whatever works for you. But I was thinking open up the yoke and just put two wheels in there. So anyway, that's a thought.
Yeah, I mean, yeah, you're right. If we hit it, it'll probably just shift the robot over.
so we haven't actually tested with the outriggers just yet.
Right, I just put them on about 10 minutes before the call started. So.
Yeah.
To be entirely honest, we haven't tested with the giant wheels anytime recently, but yeah, we could probably look into getting a larger set of outriggers. We're not sure if we're going to be able to get a new set of tires right before this weekend.
We won't. The Ninja Flex wheels will take like 73 hours to print. So there's no way we're going to have them by this weekend. And that's just one of them. So it'll take like 2 weeks just to get the 3 wheels printed.
But it's definitely something to look into.
Yeah.
You guys need to talk to your coach about getting a second 3D printer.
Go to makerspace
Yeah. But
of the printers.
so these outriggers are a temporary solution, and we know that. So theoretically, we shouldn't be having to do a lot of steering in the match. We should be okay. So I'll give you a little bit of the game rules. So to pick up one of these cubes or spheres, you have to go completely inside this white box. So before you can exit this white box and score onto this 3-tier platform, you have to be completely inside this area.
Yeah.
So this wheel, this is actually the back of our robot. I mean, I guess the position doesn't really matter because this will be the front sometimes and this will be the front. But let's just call this the back. So the back of the robot has to be completely in the square. So it only has to pass over this part twice to score one element along with the front. But we're only moving in a straight line. So,
but like I say, okay, just for grins, grab one of your outriggers and pull backwards.
Go for it.
All right.
I mean, just don't break anything, but you know, I mean, just see what happens when you push it backwards. No, but not sideways, backwards.
Yeah, so,
Okay, figure that part's moving towards you, right?
mm-hmm.
That's actually going to move towards you when you expand. So when it's going to hit, and if you really want to do it, grab it by the axle of the wheel, and then just push it backwards.
Away from you, right?
Yeah, away from you.
Yeah.
I don't know if you can see that. for this way.
I'm just saying, maybe, so,
It seems okay, Doug.
okay, it looked okay. I'm just saying, I'd be worried about that whole frame racking. And then,
Right. But they were designed so that they wouldn't hit these pipes, although they were a little lower than we planned.
Yeah, we can always bring them up higher.
another idea might be is to spring them so that they have kind of a very crude suspension.
Right.
Anyway, that would just take a spring and a pin and just let it ride up and down a little bit.
That is true.
But anyway, just I don't know.
Yeah.
I look at this and I see the extreme aspect ratios of it, and I'm concerned about rigidity. Maybe I shouldn't be, but it just seems. I owned one time in my life, I owned an Alfa Romeo Spider, and it literally bent around the road. I mean, it was not very rigid. It just flowed, and it was a fun car to drive. But on a robot, I would think you wouldn't want to do that. So, anyway, those are some thoughts.
So, Doug, did the Alpha spend most of the time in the garage, or?
It was one of the things that I would say when it ran very good. I mean, it was like a sewing machine when it ran. The problem was it didn't run very often. So anyway.
Also, Doug, the design philosophy of all that has changed a lot in the last 20 years.
Yeah.
And the idea that the frame should flex is a real no-no today. All the flexing should be in the suspension.
Yeah.
And I drove an old TR1.
Yeah.
And, it was like that. It's just woogity.
Yeah, and when you went around a curve, everything still touched. I mean, it was just like the whole car just kind of bent.
Exactly.
It was weird. It's hard to explain because I haven't driven another car like that. Anyway, it looks like you guys have made a lot of progress, especially in your material and getting the weight down and everything. Now the damn wires, I know that's always a big problem. So I mean, everybody has that problem.
The wires are the this team.
And one of these days we ought to have you talk about how you handle your wiring, because we probably could learn something from that.
I don't know.
Zip ties and dreams.
Yeah, zip ties and coffee.
Hey, I got two questions. I got one on the arm with the carbon fiber and the other on the gripper.
Sure.
So I noticed that you got these nice fancy carbon fiber arms, and if I remember right, y'all were working to CNC mill that yourselves. Is that how you did them?
Yep.
Yes.
We did it all in house.
Wow. So, and then it's so light to begin with. So was the thinking just to make it even more lighter just by carving out all that area in the arms?
Right. Again, it's a giant arm just shifting a whole bunch of weight around. So we wanted to reduce the weight as much as possible.
Well, and let's be honest.
And it looks
pretty factor.
Oh yeah, looks super cool.
It really does.
But it does actually form and function.
Yeah. And if we rebuild it, we would like to, I think, fill in all the cutouts on this specific part of the arm. You see, we had to brace it a little bit with some aluminum extrusion.
Oh.
It's channeling because the cutouts took away a lot of the rigidity. So if we ever manufacture this again, we'll fill in the cutouts, but only for this specific piece.
Well, what about making there you could just take a thin square piece and isn't there some kind of epoxy that glues carbon fiber, right?
We've also got bolt holes all up and down the arm too.
Yeah.
Yeah. So I think, Carl, what you're saying is you could make it are those flat pieces or are they U-shaped pieces?
They're flat.
Just
Yeah,
flat
if you
sheet,
made
right?
them, if you made them U-shape, you'd get a lot of that rigidity back. Surprising amount, and it wouldn't have to be much. Otherwise, instead of just being flat, it was flat where you got it now, but on the edges, you had say
You can just
quarter inch or an eighth of an
Like,
inch.
You're just saying like curling the edges.
It's just,
just take a
yes,
carbon fiber
yeah.
tube and give it some to give it some depth in that dimension with a carbon fiber
Yeah.
tube and strap it down with zip ties. You're there.
Yeah, that would give you you would get a lot of rigidity back with that.
Definitely.
That's something to think about then, definitely.
Yeah. So yeah, if you, otherwise big flat panels probably aren't the smartest. You want what do they call them? It's not a
There's a
I-beam.
T's and U's and angles.
Yeah.
And,
Oh yeah. If you take like a piece of aluminum, flat piece of aluminum, and let's say it's 24 inches long and 3 inches wide. Okay. So you got that piece of aluminum. Now somebody pushes down in the middle of it, it's going to bend.
It'll
Now, if you put a quarter inch plate perpendicular in the middle of that, you're not going to be able to bend it.
Oh yeah, certainly.
yeah.
So
So that's what they've done with the aluminum.
So you're suggesting going like cross brace or
Yeah.
or-
well, you can do it in the. I didn't mean to. The example I gave it was in the middle, but you can do the same thing on the edges.
That's what they've got with the aluminum. I'm just saying it could do it with epoxy a piece of carbon fiber in the same location. It'd be lighter.
Yes.
It'd be black. It'd look cool.
Yeah.
Do you
Otherwise, you
think
just
you could
cut a piece that's around your outside edge.
Yeah.
And then just glue it on.
If you
You
are
think
going to re-engineer it, you might think about, carbon fiber tubes are really rigid and very light and almost impossible to bend.
You think
challenge accepted.
And then
Uh,
on the gripper, so I was wondering, you talked about it driving into things and stripping the gears.
Yes.
So is the issue that that when you hit something that there's servos trying to hold it at a certain angle, open or closed, or is the issue just any kind of outside force pushing on it?
Well, the servo is actually pretty strong. It's not really the servo that we're worried about. The servo actually does a good job holding its place. And that's why I think they stripped, is because the servo didn't move, so the gears could only like move past each other. So I
So I
don't
was
think
wondering, I don't know if there's a way to let it freewheel, like a clutch or I don't know what, something that.
Well, there's RC servo savers.
Doug
You
beat
might be able to put a similar structure on at the pivot of each arm of your what do you call it? Of your claw.
Basically, what that is just like a spring clip that has a lot of tension on it to hold it centered. But if you push on it really hard, it can decenter.
Yeah.
The RC car guys use those so they don't break their servos when they slam the front wheels into a curb.
Yeah.
Interesting.
So
On the other
you
hand,
might look at that.
if you don't get all the tensions right, it could get wiggity, That might have to be done carefully.
Yeah, but you might want to look at RC servo savers.
RC servo savers.
All right, okay.
Yes.
Yeah.
Just take a note.
Yeah.
And then
RC Servo Savers. All right.
I think
We'd love to be able to do it in code. I'll say that, but with the fact that it's a servo without any feedback, and you can't get the voltage or amperage off of it. Plus, it's going through a linear cam section there. It's just not a control. We've also got higher priorities if we can fix it with physical.
Again, I think it's as simple as maybe just having it stay upright when we're moving around and only lower when we need to pick up a cube or sphere.
That might do it. But I think you also need to think of it. Okay, I made the gears so they don't strip. what breaks next?
Yeah.
My heart.
Otherwise, otherwise, now you're losing the gears. But what about the servo gears? Are they the next thing to go? You have to. You might be. Anyway, look up Servo Savers. They're very small. And like David mentioned, they're very simple. They're just basically the U clip on two pieces of metal, on two pieces of plastic. So when they're pushed, they spread the U, and then when they're not pushed, the U isn't spread. Almost any RC car today that's not a toy is going to have servo saver on its steering, because if you hit a curb with your front wheels and no bumper, something nasty is going to happen.
Right.
I just did a Google search on RC servo savers, and there's a bunch of different kinds.
Yeah.
There's even some where they just put a rod that can slide back and forth on the arm with a couple of springs on either side of it.
Mm-hmm.
I'm sure something like that could probably pretty easily be incorporated into our design.
I have seen the problem, though, that Doug described, which is that some plastic part breaking over and over again. And so I got upset and put in a metal part, and that moved the stress back up the chain. So now it broke a real expensive. So I went back to put
hard to put back into the robot part.
Yeah.
But you guys, I guess the main thing is if you lift it up, I think that'll help you a lot.
That sounds good.
Great progress, guys.
Thank you so much.
Yeah, thank you.
Yeah,
Thank you.
2 thumbs up.
Yeah.
Where's the gold star?
Okay.
That's the full one this time. Yay.
All right.
Thank you.
Saturday, huh? Will we see some video from Saturday?
There's a possibility that the tournament could be postponed due to the weather. So. But yes, hopefully you'll get to see some footage. We'll come back and show you an
If the
update.
robot moves,
If the robot moves.
Even if it doesn't.
you will see some footage of it just sitting on the field,
Yeah.
like it is right now.
So hopefully someday you'll be able to see this thing move and expand in all its glory.
It's a reach goal for sure.
Well, good luck, guys.
Until then, we're wishing you all the best because you're going to do great.
Thank you. Thank you.
Thank you.
You got it.
And we will, of course, take credit for any victories.
All right, cool. Okay, so welcome, Miguel. We're just transitioning from one person to the next. So glad to have you on board. Next in queue, we have, is Chris back on? Yeah, Chris. We have Chris, Pat, Ray, myself, Carl, then Paul, and a free-for-all after that. So Chris, what you got?
All right, so 2 things. Last time I showed, what did I show? Yeah, my waypoint navigation, right? I showed that in action. I had a video recording of it. The natural next step was to add obstacle avoidance, right? And to do that in a subsumption style kind of approach with arbitration, with an arbitration type of mechanism there. So it's actually the very first time I'm doing it in this fashion. So it's kind of interesting to see how this all comes together. And it's actually not coming together very well. And I'll illustrate here what I mean by that. So I don't have a recording, but I have a little animation sort of thing. So let me see. Share this screen. Share. So ignore. All right. I'll talk about how I did the arbitration. But first, I'm going to talk about, okay, so what's happening and what I don't like about it, and maybe Dave Anderson can give me some pointers because he must have seen this kind of behavior before. But so again, I have a target XY, right? That's my waypoint navigation, and my robot's over here, pointing in that direction already, let's say. And I mentioned I've turned my LiDAR into kind of 12 virtual range sensors, and I'm just illustrating that here approximately. So I got virtual range sensors, each one having a 30-degree cone. Those are my obstacle detectors right now. Okay, so I have three behaviors. And let me just switch to the right screen here. I have three behaviors. I have my manual control through joystick, which I've made priority 1, so I can kind of intervene, right? And 1 being the highest priority in my scheme here. Then I got my obstacle avoidance kind of in the middle, and my waypoint navigation is the lowest priority. Okay, and I can explain sort of what this Python stuff all means. But that's my three behaviors and their respective priority. Okay, and I've had the joystick stuff before and the navigation stuff right last time.
Chris,
But
may
this
I interrupt?
arbitrator here is essentially now, this arbitrator is what it's doing is it's combining all the commands from all these nodes, all these behaviors want to send motor commands, and this arbitrator is gonna decide which motor command to actually let through, right? Now, what happens though? Let me switch here to this one. Okay, so all right, so we are not in front of some obstacle, right? And I'm not trying to control the thing manually. So what would happen is, okay, we're already facing the target, so we're gonna move along, getting closer to the target. We don't have a heading error right now. We're just in a straight line to the target. Okay, so now we are within the range of an obstacle, okay? So now the avoid behavior kicks in, right, naturally. And it's pretty primitive right now, and that's maybe part of the problem. But what it does right now is, okay, well, there's an obstacle, and it's, and I'm gonna use my virtual sensors here to figure out what makes more sense, turn left or right or whatever, right? Let's say I've determined, okay, the best course of action is, you turn this way. Okay, I turn, I don't see the obstacle anymore. That's great. Avoid behavior is done, right? Waypoint navigation behavior kicks back in, and you know what it does? It says, well, my heading error is 90 degrees. I better turn back this way because that's where my target is. Oh, there's an obstacle in front of me. I better turn this way. Okay. You see where this is going, right? I get this oscillating behavior, and my question to Dave really is, well, how do you get this kind of emergent? Pretend this was a wall, right? How do you even get something like a wall following behavior that kind of emerges out of this, or in this case, something even simpler? I just want to go around this damn obstacle, and I'm just bouncing back and forth between, okay, time to turn this way, and so that's part of my thing, and then I'm gonna, so let me pause there and see if Dave has some pointers, because there's got to be some obvious way around it. Maybe it's just a matter of tweaking a bunch of my parameters, which is the second half of my update. So, but let me pause there. Dave, any thoughts? Anybody else?
Well,
any thoughts? I mean, this seems to be
yes.
like this must have happened to you a million times.
Several thoughts here. Let me get them in order. If you could rotate the robot back around where it's just right in front of the can. Okay, you actually have three zones there.
I have multiple. This is simplified. I can have as many zones as I'd like. Yep.
Yes, but using this example.
Yep.
And that fits the way the IR works on my robot, so I can use that. The speed, there's a forward component and a rotation component for each one of the behaviors.
Mm-hmm.
Now, the forward component for the center detector drives the velocity to 0. So if you continue approaching the can, the closer it gets, or the longer it approaches the can, the slower it drives. Whereas the rotation is not scaled by that distance. So if it is only centered up like that, that would basically bring it to a stop where it would rotate in place. But the left and right detectors have a forward component associated with them. They also slow the robot down but only to half speed. So if you begin the rotation here, let's say that only the front detector saw the can, and for whatever reason it began rotating counterclockwise or clockwise, left, and until about right, a little further, right there. Now the forward-looking one doesn't see it anymore, but the side-looking one does. So even if we totally came to a stop because we were centered on it, as we begin rotating, we'll begin to accelerate up to half speed. So now continue turning, but you have
So
to.
that's the part. That's where you already lost me, right? So about um, the component. So because what to me naturally what I would have done in the past without explicitly doing it sort of arbitration style is, you know, is I've kind of, if you may, merge the two outputs of the behavior into one, right? If my joystick was telling me go forward and I detect an obstacle, I would kind of merge what the joystick wants to do and what the obstacle avoidance wants to do into a new sort of angular and linear velocity. But with the arbitration, at least the way I understood it, it's either my waypoint navigation determines speed and rotation, or it's the obstacle avoidance that determines speed and rotation. Or am I sort of not getting that right? Because if the obstacle avoidance determines speed and rotation, that's why I'm not clear, right? It's going to switch back and forth between the two behaviors.
Okay, maybe it would be useful to think of the avoidance as being three separate behaviors, even though that's all coded as one. Or four separate behaviors. When there's no signal at all, it doesn't do anything. So somebody else is responsible for moving the robot forward, navigation or your control or whatever.
Yep.
But once the IR sees it, there are three possible behaviors. If the center IR sees it, it slows the velocity potentially to zero and turns one way or the other. If the left or the right sees it, it slows the velocity to half and turns away from the detection. So that means when I say slows the velocity to half, I really should say slews the velocity to half. Because if the velocity is zero, it's actually going to speed it up. It will speed up the velocity to half speed while it's also rotating. And the same true for the other one. So if you got, in this case, a right detection, you're going to want to turn away from that detection. So you turn at some fixed angle and move the velocity to half speed. So if you're starting from zero, you'll speed up to half speed. If you're starting from faster than half speed, it'll slow down to half speed. So now
So I think
continue
what
to
I'm
rotate.
hearing is I can't just stop, right? I think that's probably the crux of my mistake, and because of the simplicity of what I've done, I effectively, I guess, I stop. I don't have enough forward velocity, so I never get out of, I never get out of this sort of situation.
It's okay to stop as long as the center detector is detecting. That's really its job. But as soon as you rotate it far enough that the center detector doesn't see anymore, then it begins to ramp up the forward velocity. And that will continue to ramp up until the right detector doesn't see it anymore.
Okay, so let me put it in that position. So we had it in this position. You said, okay, at this point, the forward doesn't see it anymore.
So it's no longer, and the forward, at this point, the forward doesn't see it anymore, and it was the forward that was driving the velocity to zero.
Yeah.
The right sees it, and so the right wants half velocity.
Okay.
So it continues to rotate, but now it's moving forward.
It continues to rotate. Okay, it's hard for me to animate this, but the key is I'm moving forward, and I would have rotated it a little more.
Yeah, and move a little further forward into, now you don't see it at all. Now, this is where the problem you described happens, which is that once you're clear of the object, and it all looks so intelligent doing that part, it turns right back around and runs back into it. So the trick is you've got to get around the object before you let the navigation take control. And the way that's done, or at least a way that can be done, is with I hesitate to use the word, a ballistic delay. What the ballistic delay says, the navigation says, I'm not trying to avoid anything anymore, but I'm not going to release control for another short amount of time. And you, so it just continues doing whatever it was doing. And then after that short amount of time has expired, it releases control. Now the navigation can take over. Now
okay, so now the navigation is going to make me point back this way, you know, not necessarily turning in place, but yeah, so almost, right? And then, okay,
Yeah.
and then I've cleared, and then I can, okay.
Okay, well,
But,
watching your behavior last week, watching your video, probably what would happen at that point, you're already having forward velocity. And once you release, once the avoidance behavior releases control, the navigation behavior will slew that velocity back up to full speed. So you'll turn a nice arc and point back toward the waypoint. So there's two things there. One is that the side-looking detections have a forward component, and the other is that you have to have some kind of ballistic delay to get around the other. A bumper behavior has to do the same thing. If you think of standard bumper behavior, you hit something, you back up, you rotate, you drive forward a little bit, and then release control. So, and that forward a little bit is what gets you free.
Yeah, so I'm not making that distinction right now between, okay, I'm only seeing something in the front, or just the side, and I've cleared the front. I'm not making sufficient distinction there right now, and I have only one forward speed that I'm going to command, and it's going to be either very slow, right? And that's why I'm essentially grinding to a halt, and then I'm not clearing the obstacle. I think that's what's probably happening.
Yeah, if you, as I say, kind of think about those three ranges as three separate behaviors, and the outer two have a forward component, but the center one drives it to zero.
And the other key thing I think you mentioned is, okay, so we turn and move. Don't let go of the, even though the avoid behavior now no longer sees the obstacle, you're saying don't relinquish control right away.
Exactly. And you can tweak that value so that you have a nice clearance. I'll add a third suggestion in here, which is that at least on the RCAT, which is the most sophisticated robot, it also has side-looking sharp IR sensors. And the navigation behavior itself is not allowed to turn toward the target if that sharp eye, if the target if the IR sensor on the side of the target can see anything.
Is that part of the avoidance behavior then? Or who makes that decision you just mentioned?
Navigation. Navigation itself says I'm not allowed to turn toward the target if that side-looking IR can see anything. So the side-looking IR is also used by the avoidance behavior. This is a second use of that. And
David,
I actually added that because I have this 5-legged office chair, and I couldn't go around it. It would clear one leg and hit into the next one. And after thinking about it a while, I thought, well, I can see why it shouldn't turn there. Why can't it see? And it occurred to me that IR sensor could see. So that sensor that should be easy to do in your Ross paradigm, right? Because the sensors are not tied to behaviors, right?
That's right. Okay, so yeah.
Multiple behaviors can use the same sensors.
Yep.
That's just a tweak, but really the ballistic.
No, I think you got me the 3 points that I need to sort of look out for, and I knew all of this is going to translate into me having to tweak a bunch of parameters, and that's my other 10 minutes of my spiel is going to be about that. But Murray, I think you wanted to say something.
Yeah, I was just actually pointing out that, you were David, you were kind of reticent about using the word ballistic. And I think actually in this case that choice of a ballistic behavior wouldn't actually work in the general case. That if the object you're going around is a can or something like that, it's one thing. But what if that's actually the edge of a wall? And so I think that the case you're making is that you really do need that side IR to watch for the end of that obstacle before you can. And so there's no need for a ballistic behavior. That simply the IR on the side needs to continue to see the object, and then once the object's no longer there, then you can relinquish control. So you don't need the ballistic.
except there is a ballistic behavior on the end of that side-looking IR too, when it
Oh, okay.
stops detecting.
Sure, but I guess my point is you don't really know what the obstacle is. You don't know what its shape is. And so when you see that red object we're looking at in the graphic there, it might be the edge of a wall. And therefore, as you go around it, you may never get around it.
I think that at least in the case that Chris is describing here, if I understand what you're saying correctly, the ballistic behavior will take care of that. What the side-looking sharp detector does is, if you had the wall in your example, what would happen is you'd bounce away from it and then you'd turn back toward it. You'd bounce away from it and turn back toward it. So you would swim along the wall, which
Right.
works, and that's how most robots work. If you had that side-looking IR, it drives in a straight line along the wall because it never clears long enough for the ballistic delay. So as I say, it's a tweak. It makes it nicer because it drives straight along the side of an object, but it's not required to solve what Chris is describing.
All right. So that's excellent. So I think I know what I need to tweak. And so I knew I'm going to have to tweak a bunch of sort of parameters. And so that's why I then kind of switched gear rather than trying to fiddle with this avoidance behavior, endlessly. I decided, okay, I need a better way of tweaking parameters, which, running Python on the Raspberry Pi, it's already kind of easy, right? If you have a hard-coded parameter somewhere, Control C, you stop the program, you may edit, you run it again. I mean, it's already pretty convenient, but the reality is it's when you gotta have the ability, and I've said that before, you gotta have the ability to really tweak some of these tunables, right, while the robot's doing its thing, right? So you can really see the behavior. So even if it takes me only 10 seconds, right, if you got to take your whole robot sort of offline and stop moving, you just don't really get the right, feeling for what's the impact of the change you made to the parameter, whether it's pitch tuning or you name it, right? You got to do it while it's in motion. And so I've invested some time in learning about, okay, how is that done in RAW's land. And I just want to show that because it's actually quite easy, as it turns out. And
reconfigure.
Exactly. So there's this whole, in RAW's land, they call it dynamic reconfiguration. There's also this concept of just parameters behind the scenes. The two are related, but dynamic reconfiguration, well, like the name implies, is a little bit more dynamic. It's unfortunately behind the scenes a bit convoluted, and so most of what I ended up doing was trying to figure out, okay, how to make that a bit more accessible, the way you're supposed to do it, or at least the way it's documented and shown in examples. It involves putting stuff in a separate file, creating a package, editing some CMake file, and whole build process behind it. I mean, it's really geared towards big sophisticated robots that every feature is in its separate folder and has 3 other subfolders, and you're sticking everything in different folders, which is not what I'm doing, right? I don't want things to be that convoluted. I have all my stuff in a single folder, and a given feature is basically in a single file. Well, there's the lower layer of it, and then there's the RAW's adaptation, like I showed last time. So I don't want this elaborate and convoluted setup of files and folders like RAW's wants you to do it. So I ended up finding a way to make this parameter business a bit more accessible, and I'm kind of proud of it because if you look at this, the bottom line is, if I wanted to add a new parameter, I need to add exactly 2 lines of code, okay? So there's a little bit of boilerplate code, right, that I have to have. You got to include some include file sort of thing. But suppose you have a global, or a parameter that you may already have it in your code as a variable, right? Rather than a hard-coded constant somewhere. Usually, at least that's there, right? To turn this variable into a parameter that I can tweak from a user interface that I can show in a second, all I got to do is add this line of code, which again invokes some RAW's wizardry behind the scenes. You have to tell it about the parameter, right? What's the data type? What's the min max? What's the default value? That's kind of what's here, min max default. You give it a name, right? And then you got to add another line of code somewhere else in the callback where when someone tweaks that parameter, this callback comes in, and then you just got to pick out, well, they don't tell you which parameter changed. So you just kind of have to pick all of them out of the bunch that you get, and you assign it, to your global variable, right? Pretty unconvoluted. And then off you go, right? Elsewhere in your code, in this example, that's my my joystick interface, manual control. I have a couple parameters I decided I need. I've got my, how fast am I allowed to sort of control the robot? What's my maximum, angular velocity, and at what point do I sort of relinquish control here? Is this unrelated to sort of subsumption? This is just a joystick. If I don't use it anymore, it stops sending. I want it to stop sending sort of motor commands. And right, that's kind of all there is to it. Any new parameter translates into exactly 2 lines of code, like I said. And what you get once you do that, all right, what you get then is, okay, I have to actually, what you get is an automatically generated primitive user interface that shows you all the parameters, and it as you make changes to your list of parameters, it'll show up in here. So right now there's nothing on the left side because this stuff I was just pointing at isn't actually running. So once I start my joystick node here, okay, let me kick that one off. And okay, it's telling me joystick idle, right? I'm not using it, but it's on. And let me start my other node. That's my low level sort of motor control thing that's actually receiving the motor commands, and ignore all that output. But now these things are running. We're gonna go back to that. This RQT is a generic RAWs kind of diagnostic tool. If I hit the refresh button here, oh, okay. So on the left side, it's telling me, these things are there that are making parameters available. So joystick, the joystick makes these parameters available, okay? And my other node, makes these 2 parameters available, right? So now, as I sort of tweak these in real time, right, the updated values get sent to my running Python code, and that callback, right? Anytime I make a tweak to a single parameter, this callback here gets called, pretty straightforward. And I just take the parameters out of what's coming in and assign it to my global variable, right? And as I go through my loop, the new values will just naturally get used. And so, you get this user interface here that gets auto-generated from the information you give it, right? I told it this is a floating point, this is a floating point. I told it this auto idle thing is a Boolean, right? So it gives me a checkbox, right? You can do different things. You can do enumerations, right? But this is just the basics, and this most of the time, right? We have floating points in maybe a Boolean to turn something on and off, right? And then, so I was putting this together, figuring out how to do this because I knew to get the desired outcome from the arbitration and so on, I'm gonna have to add parameters, right, to a bunch of my code so that I can tweak things while it's in action and I can actually see it. And to just kind of demonstrate this in action, let me just hit refresh here because I don't know if the plot is updating. Okay, on the right-hand side, just for kicks, right, I threw in another standard RAWs sort of diagnostic feature, which is just a plot. Any number of ways to plot data, of course, but this is just kind of built into RAWs. I told it, okay, the red line, I told it, plot my actual linear velocity, right? And it's kind of this convoluted thing, ODOM, twist, blah, blah. It's just what it is. But that's my linear velocity that I publish because that's what I measure. That's my actual speed. The blue line is the commanded velocity, and I'm specifically printing out or plotting the x component, which happens to be just the linear velocity. And so I'm plotting this, and not that I have a lot of tuning to do on my motor speed feedback control, but to see that in action, you can see my joystick command going up, and we like to look at graphs like that, don't we? So it's ramping up. There's no PID going on here, and I'm not quite sure how to describe what's going on. It's also not feed forward like I've done previously. It's really just I'm starting out with a speed of 0. Let's say my target speed is 50, right? I'm just incrementing my motor output until I hit my target. But I'm incrementing it proportionally to how of my error. So there is a proportional component to it, but in a way at the same time an integral component, because I keep adding to my motor output power. So it's like a PI controller in a way, but implemented maybe in the non-standard fashion, but effectively it's PI. And with this I can tweak, of course, now the responsiveness, right? And I don't want it to be too responsive, right? I want it to be ramping up and down. And one thing that I'm not doing, which may be an auto, because Dave, I know you're doing it, right? You're controlling the slew rate kind of in the behavior. Right now, to me, I have only one place where I control the ramping up and down of speed, and it's in my low-level control. And that's obviously a little bit limiting, right? So I can only pick one kind of ramp up and ramp down speed, and I'm stuck with that in all my behaviors. And so I can make this more responsive or more smooth, right? If I increase the acceleration here, you could see that it was overshooting a little bit, obviously, right? So I increased the P component in a way quite a bit. So I can tweak that. Again, there's not much tweaking I really need to do here. That's not what's making my obstacle avoidance behavior ill-behaved. This is mostly stable. Again, sometimes I like it smoother, sometimes I like it more responsive, so I do need to tweak it occasionally, but for the most part it's this other new stuff that I now need to go and add parameters to, so that I can tweak it, right? Distance from the obstacle, how hard to turn. I need to add parameters for that in this fashion, and then incorporate the 3 points that you made, Dave, and then hopefully this will work.
Well, very cool. You have basically, because you can display those parameters here, you have the whole state of the robot that you can see basically at a glance, and go in and screw with whatever numbers you want. And I do it slightly differently, but achieves the same result. And and you're right, because you want to sit there and maybe run something 20 times with little tiny tweaks, and if you have to recompile, and in my case download each time you do that, it takes forever.
Yeah.
So this is very cool.
And that's one of the motivations for me to use ROS, because of a feature like this. Again, at least currently, I'm not using the navigation stack and all these other bells and whistles. I'm mostly using some of the plumbing of ROS, and these kind of diagnostic features is one of those things that again is why I'm using it, even though what I'm doing with it is just implementing fairly basic kind of a subsumption approach, right? There's any number of ways you can do that with a handful of lines of C code, like you've shown, David. But so once you have it in this environment right now, all of a sudden, you get to take advantage of some of these tools that are there, and the visualization tool for LiDAR data and my range sensor data. I'm not showing that right here, but that's obviously the other piece when it comes to sort of visualizing what's going on. And it just kind of falls, you kind of get it for free once you conform, you make your code conform to certain interfaces and so on. Then that's, again,
and from
big
your
time saver. I would expect it to be a big time saver. I mean, because up until now I wasn't doing it this way, and I really should have done this sooner.
Dynamic reconfigure is great once you bite the bullet and
twist your head around to where you can understand it. Good job. And did I hear your robot running in the background? Like,
It's sitting sitting on the bench. Yes. So it is running. It's just not on the floor. It's sitting on the bench.
doesn't count.
No.
Oh,
Right.
I know. That's fine. That's fine.
Well, Chris, in your talk last week, it seemed like that basically what you had were some fairly simple functions and then like a little ROS wrapper for each one so that they could talk to the ROS data distribution system.
Exactly.
Is that ROS 1 or ROS 2 that you're using?
I'm still using ROS 1 because there's just too many things not working 100% yet in ROS 2. Like some of those diagnostic tools and visualization, there's still a lot of gotchas as far as I understand it, or maybe they've caught up with it. So I'm not sure I have the bandwidth to switch my mind over. So I'm in ROS 1 for now.
Well, I know in the ROS 1, or my understanding is that they wrote their own message bus system, sort of like what Murray has done. And in ROS 2, they went to OpenDDS or one of those data distribution systems. If you've ever waded into a DDS, it's not trivial. And I think that the hope was that ROS 2 could maybe hide a bunch of those implementation details from the user. But it sounds like the part of it you're using is really the OpenDDS, the publish and subscribe.
Well, again, in ROS 1, there's no OpenDDS. What's behind the scenes, it's just point-to-point TCP connections, and there is a master node that kind of tells all the nodes, hey, this is who you got to talk to if you want this information. So it's actually all happens on TCP connections. It's not even broadcasts. Even though when you think publish subscribe, right, you're kind of thinking somebody's broadcasting a bunch of information and you just pick up what you want. It's not actually implemented that way. Behind the scenes, it's actually TCP connections. So if there's one node that's publishing some piece of information and 5 other nodes need it, well, then there'll be 5 TCP connections going into that node that's making that available. Right? That you don't know. You don't need to know anything about those details, right? That's behind the scenes. I'm just saying, FYI, right? That's behind the scenes what goes on in ROS 1, and it leads to inefficiencies, and there's timing aspects that are not perfect in ROS 1 and all kinds of things, right? And that's why they invented ROS 2. But for me right now, it wouldn't be productive to switch over. Right? It wouldn't solve any problem. It wouldn't make my obstacle avoidance any better if I switch over to ROS 2. It probably would break everything for the next 5 months, before I get it working again.
Well, Chris, I have great sympathy with this because if I can take a minor detour here, I was talking to my eldest son, who is a navigator on a big oceanographic vessel, and I described to him. I said, I learned my navigation skills from surveyors in the geology department at SMU, and surveyors use a Cartesian grid, and they use all angles are measured clockwise from the north. So clockwise is positive. Is that the way you navigate? And I told him that I had a colleague who had translated this into more traditional Cartesian coordinates. And so I said, is this how you do it? And he said, no, you have it backwards. And I said, oh, shit. He basically had me picture that I was sailing along on a boat, and I decide to turn 30 degrees clockwise. And during that turn, you watch the compass. You will see that it turns 30 degrees counterclockwise. So if you want to know what your new compass heading will be, when you rotate 30 degrees clockwise, you take the current compass heading and subtract 30 degrees from it. So clockwise rotations are negative and counterclockwise rotations are positive. Now this seems counterintuitive to me. Intuitive, positive. Counterintuitive, negative. Clockwise, positive. Counterclockwise, negative. But he said it's consistent. So when the boat rolls, when it rolls to the port to the left, that's a positive rotation. When it rolls to the starboard to the right, that's a negative rotation. So I thought about that for a while, and I thought I've been doing it this way for decades, and it would require changing a lot of code to switch around to from the way the surveyors do it to the way the navigators do it. And it doesn't really solve any problem. It all works the way it is. But evidently, and you were basically making it fit the way Ross wanted to see it, right?
Exactly. I had to make, when it came to all that, the waypoint navigation, I just had to make sure I make it fit the way Ross thinks of,
And Roz evidently does it the same way the navigators do it, not the way the surveyors do it.
Yeah.
You know, it would be very useful to me, Chris, if you could jot down the changes you had to make to translate that from the one to the other.
Okay,
I would appreciate that.
can do that. Let me just show one more thing. So the arbitration is actually quite simple, the way it's working. And what it end up having to do simply is, there's a and I'm just walking through this because there's one other key difference to how it's implemented on your end, David, and that's on your end. It's, you run through the loop of everything, right, and then you arbitrate, right? So there is a certain degree of synchronicity there, right? You run each behavior, they each determine if they need to or want to control, right? But the arbitrator then decides. Well, in ROS, because everything is really its own little program, right? Everything is a bit more decoupled by design, and so it's very asynchronous in nature, right? I can't say, all right, now run all the behaviors. Now let me see who wants to control and let me pick the highest priority, right? They all just happen at whatever rate they happen. And so in my arbitrator, what I'm basically doing is I'm saying, okay, look, and controlling motors in ROS means you're publishing this commanded velocity thing. So in my arbitrator, I'm subscribing to it, right? And any number of people can publish it. That's fine. But what I'm publishing is arbitrator. I'm publishing sort of the same thing, but under a new name, right? And I just need to tell my motor control, hey, instead of picking up the command under the standard name, you got to make sure you listen to this one instead. And there's a fortunately, very straightforward way to do that in ROS, kind of almost like renaming some variables. And so I'm subscribing to these things, right? So the three nodes, joystick, avoidance, and waypoint navigation, they all put out this commanded velocity at whatever rate. I pick it up here, okay? I come in, and then I have to look at, all right, well, who just published this one, right? Because I have these three publishers that all publish the same thing. I need to now determine, well, okay, so who published? What's your name? Okay. And whoops, yeah, what's your name? And then stick that information, kind of latch it, right? So that I can then use it for actual arbitration. So it's just, the data is just coming in here I'm just latching it, right? Then the actual arbitration then runs in the loop, and I'm playing with the rates here. I've chosen 10 hertz here, but in the actual arbitration loop, I then simply cycle through all the stuff that has come in, and I'm going to pick out the one that's the highest priority, and then that's the one that I then republish under a new name, right, for my motor control to pick up. So it's fairly simple. I got to look at this a little more closely. Again, as you can see here, I have to figure out what to do when nobody wants the control of the motors and so on. So there's a few nuances I need to still look at more closely. But at the end of the day, the arbitration is a very simple thing. So that's what it looks like in Python and in ROS. You just listen to the incoming data, and then you republish it under a new name. And you just got to make sure that your motor control listens to that new name.
Chris, two thoughts actually. One for you. You left a little early at the end of last Tuesday's meeting, and I think after you left, Doug asked some very excellent and pointed questions about exactly how the rotation and forward speed commands interact in David's robot, and he explained it together with the interactions with the slew. And so I would commend to your listening the last 30 or 45 minutes of last meeting, because it really
presented a lot of detail that I think goes beyond the questions that you asked tonight, and helped me at least understand the interactions between slew and each commander keeping its own track of slew, its own preferred slew rate, and what the consequences of that were in different situations. We really drilled into it in a lot of depth, and kudos to Doug for asking some really pointed questions, and we got good answers. The other just a minor comment to David's surveyors versus nautical navigation. There are really two basic coordinate frames. One is called NED, northeast down, and so it goes like this. Okay, I'm trying north, east, and down. And in this coordinate frame is used primarily by aircraft and missiles and such. And the Z, so this is X, this is Y. You're increasing X to the north, increasing Y to the east, and increasing Z downwards. And as a result of the downwards, when you use the right-hand rule, which is conventional, then the Z-axis down produces a clockwise rotation. So that's why aircraft and missiles and such rotate clockwise when you ask for a positive rotation. The other coordinate frame is used by Ross and typically ground robots, which is called ENU, east north ENU, east north up. So increasing east, increasing north, and increasing Z. Increasing X is east, increasing Y is north, increasing Z is up. And as a consequence of that coordinate frame, when you use the right-hand rule on the Z, it produces a counterclockwise rotation. So they're just two ways of doing it, and they kind of make sense because ground robots care about going up and down hills, aircraft care about going down and landing, crashing into the ground. So they're just like two different conventions. But anyway, there's some historical notes.
Well, you know, the surveyors do an odd thing from my point of view, which the roboticists don't do. If the surveyors are using a 2D coordinate system, then X is the horizontal axis, and positive X is toward the right, and Y is the vertical axis, which is also north, and so positive Y is ahead of you. But when they add the third dimension, they don't call it Z, they call it Y, and they rename the Y convention Z. So you have X and Z and an up and down Y. I have no idea why they do it that way. It makes no sense at all to me, but they've been doing it that way for hundreds of years.
Yes, and I ran into that on a TopCon total station, and you're right, surveyors don't actually use ENU or NED, they use END, if I remember correctly, because no, they use NEU. They're like different than the two standards. So
and that just happens to be the people in the building when I was teaching myself navigation 30 years ago that I went and asked the questions to.
Anyway, nice demo, Chris, on the
excellent. Yes, excellent.
On the dynamic reconfigure. Good job.
Chris, did you get a chance to monitor what the people in the home robotics group are doing? You are
I've looked at it a little bit, but not very closely. So I just subscribed to it, but I haven't really.
Well, you are way ahead of them. They might just to lay out how your devices talk to each other. They're trying to hammer out that level, but they're also, in my humble opinion, trying to work out a full design, and I think that's problematic.
All right, thanks for all the feedback.
Cool. Looking good, Chris. You're really sending some motivation to think about Ross seriously with all of the. I mean, there might be a learning curve to get the first few steps in on the infrastructure, but once you get the plumbing, I mean, these demos you've given week after week are okay. When I get to my part, I'll show you the UI I've been thinking about. But it strikes me that we spend a lot of our time just worrying about how do we control what we're building. And understand what it's doing when it's on its own out there. So, okay, I think next in line we had Pat, Ray, then myself, Carl, and Paul. And we need to make sure, because Paul, we pushed you out towards the end last time and we ran out of time. So we are not allowed to do that this week. We're going to do whatever it takes. Paul, you're going to get through your stuff tonight. We're going to help you do that. So next we have Pat. How are things going up there?
Oh, making some discoveries. So I'm going to see if I can present and share my screen. And so basically, I've got the Raspberry Pi talking to a couple Arduinos. And on my center window, you can see what's going on. I got to stop that. So you can see that my user applications are taking 74 or 75% of CPU time. And my idle time, while it's running, my programs are running, I'm down to approximately 2%. So I'm wondering, is anybody else running on Raspberry Pi 4 seeing the same thing when they're running Python programs? Controlling their robots.
Well, you said you're doing some stuff on serial ports.
I'm using 2 serial ports.
Okay.
And
okay. So actually, before I get there, because when it comes to serial ports in Python, there are some inefficient ways of doing it, and I ran into that, and I had to do things differently in when I process the data, but one thing, if you run HTOP, I mean, do you have a sense of who is actually using the CPU time? If you just run HTOP and let it show you all the threads and everything that's there, I don't know if it's going to give us any new information or more information than you have right now, but right now you just displayed the total, right? You know, in total, it's super busy. I'm just wondering, again, if you run, and I prefer HTOP over top, at least you get confirmation as to who is using the time, because it's going to be your Python stuff for sure, but it's also going to be, it seems like you're running, you're doing a VNC session. You're running flat out there 100%. You're doing a VNC session. Okay. No, but that's not what's using the time. Well, it's using half of one core there. You see that XORG, blah, blah. There's definitely the user interface stuff sucking up a little bit of time, but on the top, yeah, it's really all your Python stuff sucking up.
All my Python 3 stuff.
Wow.
And so that's why I wondered if
there's got to be, I can't imagine you crunching a huge amount of data here. So either you're doing something with the serial ports, using some easy to use libraries that are, or APIs that are unfortunately very inefficient for, things related to, I need to read one whole line of data from whoever is sending it over the serial port. Things like that I found to be very inefficient, and you gotta go down to a slightly lower level sometimes. Or you're sitting just in a loop here, spinning at 1,000 hertz or something. I mean, what's your loop rates?
My loop rates are 20 hertz. And typically I'm idle. So I just sit and wait until my milliseconds expire before I run my routine.
How do you wait?
Is it blocking code?
No, it's not blocking code. It's just waiting until the milliseconds are exceeding.
Specifically, how do you wait? What do you call to
What's
wait?
the line of code? What line of code do you use, or 2 lines of code to do the wait? I hope it's some sort of sleep.
What's that? It's not asleep.
Well, that's your problem.
That's the problem.
Okay.
Blocking.
It's
So I
spinning,
should be
queuing up CPU cycles, doing nothing in a while loop. You need to put it to sleep for a while.
okay. So if I go to sleep, my next question becomes, and I haven't looked into sleep very much, but if I do my calculations, figure out I've got so many milliseconds left till my next loop time, and I put it to sleep for that many milliseconds. If I have a callback on a serial port or like a callback routine, is the sleep blocking? Will it prevent the callback?
The callback should still happen, and I'm not using callbacks really except in the RAWs stuff, and you do the sleeps in RAWs, and it still calls the callback. So outside of RAWs, I mean, the same thing is going to be true.
When you say you've got a callback, what exactly do you mean? Because you typically don't use a callback in Python for serial I/O. Are you talking about like an interrupt happens because some data comes in?
I believe I'm using a callback. Hang on, I'll see if I can pull it up. Open workspace from a file.
Pat, in general, when you call sleep, it's only the thread that's calling it that is sleeping.
Yeah, so I'm not calling sleep, so that's part of my problem. The easiest way is I'm just going to get out of this and shut this guy down and open up code. And go to, where's a routine? So I'm using, let me share my screen again. So I am using, it's in Python, and I have an on message callback routine. And where is my message, my callback?
So you're using some sort of library here for all this serial stuff?
I'm using, it's an MQTT library.
Now, Pat,
Okay, so the callback has to do with MQTT, not with the serial port.
Yeah. So, and I've got this one is sending serial to the motor, and it's receiving by MQTT. So basically, what I'm doing right now, I'm just delaying. I'm spinning my wheels with a millisecond.
Yeah.
Yeah.
So what I should be doing is instead just put a sleep at the bottom and just delay, just sleep whatever milliseconds are left between from coming into this routine till the end of it.
Behind the scenes, I'm pretty sure that this MQTT stuff that you're doing through some libraries is going to spin off some threads, and they will run even when you sleep here, and that's what's going to call your callback. So I'm pretty sure of that.
Okay, well, that's what I'm going to test. So it was one of the questions I was looking to go next, is saying, okay, well, maybe it's just because I'm sitting there spinning, waiting for milliseconds to expire. And yeah, that does take processing power, so it's going to be constantly using CPU cycles. So that's a good step towards trying to resolve that, and it's fairly easy to implement. So I wasn't sure if it was MQTT that was slowing it down or what it was. So I put another one on it. I put RabbitMQ on, which is another routine, which incidentally I think behaves a little bit better MQTT is a first in, first out messaging bus. So if I put in a message from my joystick, and then I put in 50 milliseconds later, I put in another message, and 50 milliseconds later, I put in another message. And after 10 seconds, I connect to the message, say, hey, is there any joystick messages? I get the oldest message that's still in the bus that comes back. And so when I switched it over to RabbitMQ as a test, I got the last one that was sent. So I ran everything for, it was like 10 minutes. And then I joined it, and it was instantaneous. I got the very last message that was sent.
You might look at queue depths, because typically, at least in ROS, you can set queue depths. And a lot of times in ROS, you'll set the receive queue depth to 1 for those kinds of messages. And it sounds like maybe in MQTT, maybe you've got a deeper queue depth, so that's allowing those joystick messages to accumulate. But I bet there's a setting that you can set on that.
MQTT, no. So I can set quality of service and get an acknowledge on the message, but I can't control the queue depth as far as I know in MQTT. So I can't limit it to 1 for queue, for a queue depth.
Wow.
But I can do that on RabbitMQ.
Okay.
And on RabbitMQ by default, it'll send you back the last received value, unless you tell it to send you the first in, first out.
Oh.
You know, this is a problem we've talked about before, which basically has to do with data loss. If you think in general about FIFO queues are designed so that if the data is coming in faster than you can physically do with it, you don't lose any data.
Yeah.
But on robots, really, if it's coming in faster than you can deal with it, you just got to throw it away. What
you need a queue size of
really
1.
need to queue it up. You need the most recent one. If you didn't get to it, it's just gone. And so there's some problems. And as Chris was describing, you know, the queuing. Paul. The queuing introduces its own latencies, and so depending on what you're trying to do, that can be problematic.
It is application dependent, though, David, depending on exactly what you're trying to do. Sometimes you absolutely do care about the message and must not lose it, and other times you should throw it away and just take the latest. It depends.
When I was first getting the two-wheel balancing robot to balance, and I had made some changes, and it had gotten real squirrely, and I went back. I just couldn't get it readjusted, and as I looked, I realized that what had happened was that I was now going through a serial queue. And that serial queue introduced just enough latency that it wouldn't balance anymore. Yeah. And I got rid of the queue and just had the interrupt talk directly to the algorithm, and the latency went away and the balance came back. So yes, very much application dependent.
Yeah, so that's why I was looking into what I could do to replace MQTT as a background application. So basically what I do is I launch from a terminal bash shell, I launch all of my terminal, my Python applications separately. So they're all running as an independent process. And I use MQTT as in the background as well to communicate through between all my processes. And overall, it seems to be working okay, but I've got the problem with the FIFO. And like I say, if I look at RabbitMQTT or RabbitMQ, sorry, it's basically it'll eliminate the problem. I can get last in, first out. So I can also set a queue size. Just give me a queue of 1, and I'll always the latest.
Sometimes you could be using ROS.
I'm at this point. I was toying with the idea. Because I did dabble in ROS a while ago. Do I turn around and just go back and report my Python programs to ROS? So, you know, I've still got a ROS application on my phone as a remote control, and you know that
seems like if you can choose between whether it's first in, first out, or first in, last out, then you can tweak that to whatever the circumstance. That seems like the best of all worlds. I know the code that Paul was working on in order to measure very sparse encoding ticks. You can't you have to have everything queued up. You can't drop any of those. Same thing if you were trying to calculate position or something, you can't drop anything. But in other cases, as I say, if you're looking at a sensor or something, if you didn't get it, you just didn't get it. You know.
Yeah, and I'm running my my serial ports are at 115 kilobaud, and I am sending quite a short message. In the worst case, I think it's 100 bytes is the longest. So it's not, you know, very much code at all that I'm sending back and forth. I'm using a serial transfer library that I found that'll it basically sends it all out as sort of a packet, and that seems to be working well as well. But like I say, I'm just running into the problem where I have no CPU cycles left. So I showed you what I got with, you know, less than 2% free, and I haven't added any video processing in there.
Are you using packet serial by any chance?
No, I'm using a serial transfer.
Okay.
So it's a fairly lightweight application, and it can send all sorts of data. It can send string data, integers, all sorts of different things. And it's fairly lightweight.
Well, you need to give us a report if you substitute out that delay where you were just spinning on memory with an actual sleep, and see how much CPU cycles you get back. That'd be very interesting.
Yeah, everybody saw I had 2%, less than 2% typically left. I'll rewrite some routines. I'll do some tests this week.
Come back to you got 90% left now.
That's what I'm hoping, because it's having 2% left. There isn't much room to play around, and you add all sorts of bugs and latency and everything else into the program.
And I'm curious on your learnings with RabbitMQ and MQTT. So those are very interesting to me as well. So
yeah, that was on the weekend. I played around with RabbitMQ and just created basically like a publisher and subscriber. Actually it was on topics I used.
Yeah.
And basically just turn around and wrote a couple routines. I let the publisher run for about 10 minutes and then start up the subscriber, and right away I get out the exact same numbers I'm publishing. So it's when I stopped the publisher, my subscriber immediately stopped at the same number. So
cool.
That looked like it was working okay with RabbitMQ. So a lot of digging around, trying to find something to communicate and trying to find something to get out of the 98% CPU usage. Because at this point, I'm going to need a cluster of Raspberry Pis to be able to run this thing.
And using that pattern, they might all be doing this most of the time. So
exactly. So, thanks for the input, guys. It's good with the sleep as opposed to just looping through the milliseconds.
It looks
But
like
keep in mind your VNC session is also going to use up CPU, so that's not your problem right now. But at some point it might be, right? You were doing all your user interface through VNC. It is going to suck up some time, especially if everything is constantly updating on the screen.
Yeah, so eventually it won't be updating on the screen. I have troubleshooting, so I set a troubleshooting flag in all my routines, so it is printing to the console as well. So typically I turn that off and nothing is printing to the console.
Looks like serial transfer is another flavor of perhaps a family of transfer packets like packet serial. It also uses constant overhead byte stuffing, which I went through when I explained packet serial a few weeks back.
Okay. It was just something that I had found, as opposed to just creating my own string and everything, because there is some I believe there's some, not error correction, but there's
they protect it with a CRC.
Yeah, it's CRC protected, so it'll know that, hey, it's the wrong message, so ignore it.
Yep.
So if you're going to lose a packet, it's better than getting the wrong packet.
Right. Cool.
Okay, thanks, guys.
Thank you, Pat. I think next we have Ray. John snuck in with a 2-minute update. Carl and Paul. So Ray, what you got? And mute. You got a mute button there, Ray.
Yep.
Yep.
Okay, I'll start over. And now for something totally different.
And now,
I've been working on kind of a small mill. The Bridgeport is showing its age. It's got a 2x20 LCD, and it tells you a lot about what the machine is doing. And that is starting to go out. It's got like a blob in the center that kind of blocks out some of the things. So I wanted this simpler machine to do, quick stuff like make brackets and, mill large holes and that kind of stuff. Anyway, so those things typically start out with the old graph paper mechanical design where you put all your dimensions on, and you have to translate that into some CAD program. But you really have to start out with that, or at least I do.
so you start with the graph. You start with a graph patterned napkin.
Oh, graph pattern. Yeah, this is 10 squares per inch
Excellent. Okay.
graph paper. I've got a whole roll of it. It'll outlast me.
Ray, a question. When you say a small mill, are you saying, 1,500 pounds versus 3,000? Or are you talking about something I could pick up?
No, not unless you're like Arnold Schwarzenegger. I think it's probably at least 200 pounds, maybe more.
And your big one's like 1.5 tons or something, right?
Yeah, it's like 3,000 pounds.
So when you say small mill, I think of those desktop things you buy for like $300.
No, much bigger than that. Anyway, I did a video of it. Well, one of the things that I try to do on this small mill is actually mill out, just to check things dimensionally. I tried to do it on it's a 30 by 18. I think it's really good for, making printed circuit boards and that kind of stuff, because the bit was just melting this acrylic plastic, and it did these 2 holes, and then it went to do this thing, and I think it got heated up, and it started moving the piece around on the mill, and all that stuff. So it was kind of like, okay, that's useless. So then what I did, I have a video. Oh, where'd the video go? Oh no. I had a video up here. Well, had a video queued up and it's disappeared. But I'm sure I can find it again. Okay. Drive. Pictures. That's probably it right there. Okay, this is what I've been working on. I made okay, I gotta stop it.
We heard it.
Yep.
Just share it. Yep.
Yeah, I started it. Hold on a second. Gotta get back to this. Cut that out. And go into present now. Entire screen. Share. Okay. Can you guys see that?
Looks great.
Okay.
And this is the
Anyway,
small
so
one or
this
the
is-
Bridgeport?
Say that again.
This is a small one?
Yeah, this is the small one. The
Okay.
Bridgeport is like 7 feet tall. I need a freaking ladder to work on it. It's so big. Anyway, so it's basically an XY table, this thing here. And there were two stepper, one stepper motor on each axis. But I didn't have a Z axis, and that's what that plate was for. And I wanted to basically put a bearing on it so I could put tension between the sprocket on the motor and the sprocket on, I don't know, I guess you call it the quill feed. So there was tension on it. So, there wasn't any backlash. And so to mill that plate out, I was acting as the Z axis. I could look at the codes coming up, and I would, it's, not calibrated at all, but I would just force it down into the metal a little bit more so it would hog it out. And it made the plate, and it actually did really well. I was surprised by that. But anyway, this is working on. I made basically a milling machine out of the old Rockwell drill press, and I had to make this plate that's got a stepper motor and a set of chain sprockets and a bearing, and the angle that sits at puts tension on the chain so it's not loose. And this was driven by two 300 ounce inch stepper motors, one for the Y and another one for the X. And that's driven by an Arduino Mega with a ramps 1.4 board and individual power supply, or not power supplies, motor drivers there. That's the power supply for the motor drivers, and that's another one just for the Uno. That's a little interface. It's actually a Mega, but that is, you can download files. Anyway, I use this to cut this plate out by drilling holes and cutting out large circles for the bearing and for the front of the motor. Anyway, that's what I've been working on. Anyway, so that's what I've been doing.
So when you cut out that plate, you were basically allowing the CNC to control X and Y, and you were manually Zing?
Yeah.
And that worked?
Yeah, it worked really well. I could look at the display and see, how much of an increment I needed to go down, and it's,
But you weren't just guessing when to do it. You were following the machine code in terms of when to do it.
Yeah, because it would say what the next move was, in X, Y, and Z, and it was only down 1/10 of a millimeter, so it's it's very small. But I didn't want to be too aggressive because I couldn't follow it that closely. And when the thing was finished, I had to be up and out of the way because it would have assumed that the Z axis moved the tool out of the way and stuff like that. So
for some reason, that just strikes me as really cool. I immediately think, well, I want to see both X and Y axis also driven by humans, and it's performance art. It's complicated 3D shape.
There you go.
And it's also dance, right?
Yeah. Maybe it'll show up at Burning Man. I don't know.
Just needs the music in the background.
Yeah.
Yeah, it's not very exciting. I had to stand there for almost an hour because the increments were so small. It's kind of like, oh God, I hope this thing. And I finished way before it finished, so my uncalibrated tweaks were much bigger than 1/10 of a millimeter. So, but it did okay. It did throw two pieces out, but when you get to the end and it just grabs it and goes, whing, But it missed me both times, so survived. But yeah, so just to do simple brackets and stuff like that. I don't know that it seemed to work well with like 6061 alloy aluminum. I don't know if it's going to work that well with steel. It may not. But most of the things that, I can do in aluminum, that's fine. So,
I wonder
but
how many people with 3D printers are guilty of staring at the printer print for long periods.
oh, just watching it print there. Yeah. Oh, that was the other thing I did. There was Thingiverse. I don't know if Murray's still on, but they made some guy was very creative and made a very neat little enclosure for the LCD, which is, back half and front half, and then a spacer. Even has a little reset button on the front of it where the reset button is. And so, I Thingiverse is always amazing. I don't know how much time those guys spend on creating, those objects, but it certainly saves me a lot of time. It's kind of nice just, you type something down, I typed in 128/64 and it knew right away what I was looking for, because that's the resolution of that display, and that's what's used on, the 3D printers and the simple CNC mills, and it's like page after page of examples, and you just pick one and print it, and you got a part in a couple hours. But anyway, so that's all I had to show. So it was actually a lot of fun to do it, but the challenge.
How long did it take you to print that?
The bottom half and the top half were each about 2 hours, and the button and the little spacer probably about a half hour.
Okay.
And that's on real coarse. I think that was I think 0.4 millimeters for spacing, and that's I think that particular nozzle was only a 0.5, so that's really coarse. You get, you can see a lot of the individual lines in it. I don't know if that'll show up on my camera or not, but that's where you get like the kind of the cross hatching when it fills in. Otherwise, I could have done it, I think it was either 0.2 or 0.1, but it would have been over 5 hours for each piece. And I was like, nah, I'm not waiting that long for this thing. So it's coarse, but it works fine. So
Reason I'm asking, I did one of these just for my desktop.
Yep.
And it printed pretty good, but that's 17 hours.
Oh yeah. That's probably super fine resolution, right?
Yeah.
Murray could have it shipped to New Zealand in that amount of time.
Yep.
Lately, nothing is shipping. My Amazon Prime is a week out.
Hey, I got this after only a few months.
Oh, is that your oak light?
I came yesterday.
I have one. I did a Kickstarter with Mycroft. It's a Raspberry Pi voice home assistant thing. Mm-hmm. So the idea is it's decoupled from anybody listening to you or watching you or whatever. And so I backed this 2 years ago, and I'm still getting updates. They're talking about shipping in September 2022 now.
Yeah, but I think what David's talking about is the shipping part. Like the Oak D thing, they, as a project, came through pretty quickly and got it shipped. But once they had it shipped, it still took me 5 weeks to get it.
Yeah, that's out of China. Anything AliExpress right now, I've got a couple things, and I'm still waiting.
So I think the people who were trying to convince Murray that he needed to get into 3D printing took the wrong tack. They should have used shipping costs and delay as the main.
As a selling.
I have to say that the cost of a 3D printer in this country and the cost of the plastic stuff is extremely high.
Well, I was thinking you would say that okay, it took 17 hours to print this, but that's quicker than 2 months to ship it.
Yeah.
So you talk about that, Murray. You talked about building with that plastic sheet Delrin, I think you called it.
Yeah.
So I looked up Delrin to get it here. The only way I can get it is Amazon. and it would be quicker to gold plate my robot and cheaper.
Do it.
Pat, what's the closest big city you're close to?
Sudbury, Ontario.
I'm absolutely convinced that Sudbury or someone in Ontario is a plastic supplier, because I'm just getting this from a shop up in Auckland.
I buy mine from the local glass shop here in Denton.
So Toronto has them. I could find it online in Toronto.
Yeah, just a regular glass shop should have it because they make tabletops and things like that out of it.
Out of Delrin. Oh. Well, put it this way, it's a small shop up in Auckland, and it's probably closer to you to Sudbury than it is for me to Auckland. And this guy is a German guy with a funny accent, sends me Delrin in different, I just got a package of it a few weeks ago. I got polycarbonate for the front bumper and Delrin this is for the Mars rover. And it's not cheap, but it works really, really well. It cuts like butter. It never snaps, or, it's great stuff.
I've been looking on Amazon for a 1/4-inch piece, 12 by 12.
Don't get it off Amazon. Go off a plastic supplier.
But you're right; it's real expensive.
It's $100 for that little piece.
Yeah.
What?
Serious? 12 by 12 1/4-inch is $100.
Canadian.
Yep.
That's more expensive than I'd pay.
That's what I'm saying. So, and then it's a 5-hour drive to get to Southern Ontario, Toronto, to get to a plastic shop that would carry it.
Because this is like thicker than quarter. I think this is in millimeters. This looks to be about, maybe this is 10 mil. And I can't remember what I paid. I bought 2 of these because I put them underneath I use them as carrier boards. And it's also, incredibly, you couldn't destroy this if you tried. I think this costs like $7.
Wow. Maybe you should mail it to me from New Zealand.
Yeah.
So now you know why I built the one.
We're down a rabbit hole. So, Mr. Chairman, would you care to reconvene us?
Yeah. So, all right. Okay. So we can gripe about delays in shipping. So we need to move on because we have to keep Paul on track. Thank you, Paul. So, John, you said you have a kind of brief one. Mine shouldn't be too terribly long. So, what do you got, John?
Yeah, if y'all remember from last week, I had my animatronic eyes that I borrowed the design from the web and built, and mounted a camera on it, and I was having it follow my face using face tracking software. But I was really unhappy with the performance. It was like, every from a half second to maybe 3/4 of a second per frame, and the eyes would just go click, 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 click like that. Not very realistic. So I got an Intel Movidius neural compute stick. Actually, neural compute stick 2. That's basically it's a little video processor on a dongle that you just plug in the Raspberry Pi's USB port, and there's a OpenVINO toolkit that you download with it, and now it's humming. I mean, it's like 20 times the performance now. I'll show you. Get the screen here. I've also got the image is a little bit bigger now. Now you can see the box that's tracking my face. It's not jumping around. It's moving. And you can see the eyes are just. I also made the video for the cracking the eyes a little bit bigger so you can see it. That's pretty smooth, huh?
How much does this little box, this little dongle cost?
About $74.
Ooh, okay.
Yeah.
So,
not cheap.
And that's what I have. If you have a project that needs a robotics project that needs so to recognize objects and follow them, that neural compute stick will definitely make it worthwhile.
John,
that's on a Raspberry Pi 4, which I thought would be fast enough, but without the neural compute stick, it's just not fast enough.
John, could you put a link for that in the chat?
Yeah, got it right here.
I thought you were using the light for, to find, your face in the image. So you weren't. You were just using a Raspberry Pi and OpenCV?
Yeah, a Raspberry Pi and OpenCV.
Okay.
So let's see.
Did you have to compile any routines for OpenCV to use their neural compute stick?
No, I'm using the instructions from Pi Image Search. It's one of his free tutorials, and it was pretty easy to I mean, there were a few nits to work through, but he gives you real good step-by-step instructions, and it was pretty easy to use. I only had to add like one line of code into my existing program to use the neural compute stick. Well, in addition to, there was a few extra lines of setup as well, but it was pretty easy.
Could you share the link to the image search tutorial?
I'm sorry, what?
Could you send a link to the Pi image search tutorial?
Oh yeah, I've got that up right here too.
Probably just go to their thing and put in neural compute stick. It'll probably come
Well,
up.
he's got a whole bunch of articles, so this is, you got to be sure to get the right one.
Yeah.
This one is the pretty much the most basic one he has on how to use OpenCV with the Movidius neural compute stick.
Did you have to did you have to convert the model format with OpenVINO, or does he already have that?
No, there was already sorry, there was already a CAFIA model that you can download for detecting faces. And there's a whole lot of free models out there for different things like, cats, cars, whatever. There's plenty of models that other people have built that you can borrow.
Yeah, I got one for Christmas, so I was real excited about that. I had the old one, the Movidius first stick 1, but
Yeah, that's
they've dropped the support of that in OpenVINO.
Yeah,
so
that's what you got to be careful of.
Yeah, you can still use an old version of OpenVINO that's still available, but when I used it on a Pi 4, I was getting this was the 1. The acceleration was about 9x, and I think the 2 is 20, about 20.
Yeah, I bought the 1, as a matter of fact, and returned it on Amazon when I realized that the current software didn't support it.
Yeah.
So I bought the 2, and the 2 works just fine.
Yeah. I can't wait. Yeah. Cones.
Yeah, it'd be perfect for something like cones, but it's especially useful for something that moves too.
Yeah.
Cool. Well, looking good, John. So we got a lot of camera progress in the club now.
Okay, guys, question. Before, just because I stepped out for a brief, I got Iron Rain getting a black star. Does John get a black star? His eyeballs are moving.
Black star.
His eyeballs are moving.
Eyeballs are moving.
Okay.
Well, it was an incremental improvement because I showed it last week. I got the gold star last week. I can only get a black star this week.
Yeah. And who else? Did I miss anybody who's already? What about Chris? Chris was working on. He showed some progress.
It didn't. No stars for me. It's fine.
Okay. All right. Okay. So I got Iron Rain and John G so far. If I'm leaving anybody out, just let me know. Okay.
All right. Okay. So next, I'll try and be fast here, and then we'll go to Paul, and hopefully, I don't think this will take too terribly long. This is a non-star presentation, but I started to think about what I'm doing next, and I realized that I needed to step back and think about when am I going to put the duct tape aside and start to do something that can scale like with a better architecture. So I think in PowerPoint these days, and I started to realize I got all these options, right? And there's a lot of shiny objects, right? Because over the years, so I thought, well, whatever I do this year, let's start with the shiny objects I have already got, and then let's piece them together. So I got three piles of shiny objects, right? So and most of these, I think I have all of these on hand except for the Cutie Pie, and I've at least turned most of them on, most of them. But it was interesting to sit down and pull these together. So these are the options that I think they all have enough horsepower that you could drive a robot with them, depending on how much you want to do with it. We all familiar with the Raspberry Pi. It's got a Broadcom ARM V8 quad core. This OpenM VH7 is kind of nice. I didn't realize till I looked at it for this slide. It's got a STM micro something or other. And then the Mega and Nano, I keep saying I'm done with them, but I got a lot invested in them in time and libraries. And the ESP32, a handful of us have those, and they got a pretty spiffy processor and memory footprint, and a lot of decent I/O and wireless connectivity built in, and cheap cameras built in, and Cutie Pie is also pretty fancy, right? And then I've been for years intrigued by Espruino. So this guy out of the UK who's made a kind of a port, I think of it as Node.js, JavaScript Node.js. And he's made it where it's very efficient to run on like really lightweight battery powered things. So like this and this and this run Espruino natively, and they got some decent processor capabilities. So I got all these things to choose from, right? And then we step to cameras. Well, okay, I've used this for the donkey car, the Pi with that camera. I used this on the outdoor rover thing with the duct tape and baling wire one. Bought some of these, is just sitting there. Bought this one, and it has some Ovidius buried in there in its bonnet, but I haven't done anything beyond power on. Its joystick is a joy detector, right? Is somebody smiling or not? And then this just came from the Kickstarter, but so many shiny objects. And then we come to UI, right? So here's Chris with his fancy ROS, nice network connected palettes and stuff. And here I've been buying all these stupid little gadgets and displays and switches and knobs and potentiometers.
Nixie tubes. Use the Nixie tubes.
I just really like the look of Nixie tubes. So I have some boxes of numeric digits. I've got these bar graphs things I want to put in there. I haven't got any Decatrons yet, but they're calling to me. But these others have a dwindling supply. So I've already got a lifetime buy of those, sort of. And e-ink, it's just slow to update, but it works so well in bright sunlight, right? And then these watches, right? So they run the JavaScript and they run on batteries. You can put them on your wrist, and they have accelerometers and decent display and touch screens. And of course, this guy and these, I think you can't beat the quality of the potentiometer. Nice. It's hard to beat a good joystick, right? A nice response. And then there's other things we tend to play with. So like these OLED displays, the traditional alphanumeric displays. And then this one just caught my eye because this would look good with steampunk. I think the transparent display, you can see through it unless when you light it up, and then it's got the characters and of course the neopixels and push buttons and electroluminescent strips. And then up here in the top corner, we got Node Red. I mean, think of all the things you can do with Node Red: dashboards and graphs and controls and knobs and switches. And then you've got the web apps, right? So we, like early on in the telepresence thing last year, someone found the project where you could use Amazon Web Amplify and Vue.js and come up with a nice web. All right, so many shiny objects, so many. There's just too many of them. So I figured, okay, so what if I got to do something this year, and it's just imagining in the context of an outdoor rover, and hopefully it's a platform that can scale like different ways. But if I think about outdoor rover, so this is what I'm thinking. And there's another reason that I'll share it later on. I've been inspired by Jack in the presentation he's working on, actually. So I'll follow up after him with something like this. But what I'm thinking is take the Oak D-Lite. It wants a USB interface and something a little smarter to talk to it. So I figure I'll connect it to a Pi 3B because there's some of those floating around here. And then I've already got this kind of thing set up. I've got some libraries. I've got my own libraries, so I have a nice non-blocking way to reliably send packets at a pretty decent rate between these. Even even with the Pi as the master and this is the slave. So as much as I want to run away from Arduino, I think I've got a code base that says I'm going to stay there for a while. And then this is leaning on it's weighted towards things I've been wanting to play with, and I haven't found a good excuse yet, basically. So really, I think a lot of this exercise is going to be these links over here. So the idea is that these things right here at least provide a good kind of a, what's going on with a status indicator for the Mega, and at least one button to stop it if I need to. And then the Pi, where the real brains would run, well, that thing, for development, you could use real VNC, SSH. If you want to run it over the web across the network, or even connect to its own web page, then you can use Node-RED. Or then if you don't have a network around and you just want to control the robot, well, this guy is kind of nice because it's got a 128 by 64 sunlight readable display. It's got 4 buttons and a decent enough processor. So I think that could be a pretty nice onboard control and display. And then when it comes to remote, I really want to play with this latest watch. And I think that I can get a bi-directional interface going over BLE. So I can have high-level mode control and status on the watch, wearable. And then I can have, this has a multi-point, I don't know how many points, but more points than your finger size would allow. So I can do a lot of things with a touch display just on this watch. Have that send messages to this guy, have that relay it to the Pi, and so I can have a wearable control. And then this guy, we talk about on the Rolo Magellan being able to grab it if it starts to run away. So I'm thinking I got way too many of these. I overbought these from the Kickstarter. And then another one came out, and they're all very similar. So I'm thinking I use this as a dead man where as long as it's broadcasting and this is receiving, then like I can have a hardwired digital I/O here that just enables or disables the motors. And if this guy ever stops broadcasting, then it'll pretty quickly just shut the motors down. So anyhow, that's so many shiny objects, and if it's of any value to you, it was an interesting exercise to look at the different capabilities and that have accumulated over the last 5 years and think about, okay, what now? And it's funny to me that Chris was showing all these fancy things that you can do with ROS, and I'm going, damn, there's another shiny object that's not anywhere on here. So I'm looking forward to, I think somebody, I won't name any names, but somebody's volunteered to do a kind of a ROS little workshop to get started. And that's all I need is another shiny object for this year. So I'm looking forward to that.
It's interesting that you if you keep that slide up, it's interesting that what you're building there, what you're proposing there, if you swap out that Mega 2560 and use a Pi board, which is what I'm doing.
Yeah.
I'm actually almost, it's exactly what I'm doing. I've got a web, I'm using that little, what's it called? The little gamepad, which is Bluetooth. And apart from that, I'm using a Pi 3B Plus. I just got my Oak D Lite. My connection is actually over I2C, but maybe SPI to a Pi board. And then my stuff's on the Pi board. That's actually my current plan, or what I'm already doing. Although I did say in email that I think that my Oak D Lite's going to have its own battery supply because it's one.
I didn't know this when I bought the compute stick, but it's got the same VPU as the Oak D Lite does. So I guess it's just basically an Oak D Lite without the camera and without a lot of the extras.
All the IDE and the built-in everything in there. Yeah.
Carl, one comment. I understand your familiarity with the Arduino libraries has pulled you toward the Mega there. But if you would put in that place any of those ARM controllers you showed, the ESP32, the STM32,
any of them.
The advantage you get is that the ARM hardware has a whole bunch of stuff in hardware that you need to do on robots.
Yep.
It has that all run in the background and take no CPU cycles. That includes quad encoders and generating pulses and decoding pulses and all kinds of things. So as a path into the future, which is what I imagine that you're putting together here, you might think of replacing that Mega 2560 with a more modern, more capable.
You know, David, the only thing that would prevent me, I realized that on one of this weekend's bike rides, which is another story. The only thing that's stopping me from doing that is the next step is that I have this nice Club 2016 Club Robot platform that already happens to have the Mega and the Pi and the interface in place.
So decision made.
I mean, yeah. So I can expand the architecture a lot wider, and I can do this. I can use this as a development platform and worry about improving and cleaning up the inaccessible guts down here later.
But to follow on David's point, one of the reasons that you cited for sticking with the 80 mega is you've got a lot of code already built for that, and if you use the ESP32 running the Arduino environment, then you probably most of that code will still work.
I was wondering about that. I'm very glad to hear that. So that's definitely in the path. Yep, but that requires more compiling, or hardware changes even. So,
I'm using these little. It's kind of funny because, Paul, as you say that, I'm thinking like I've been using the little tiny Pico, the Unexpected Maker Tiny Pico, and that can run either CircuitPython, MicroPython, or C++. Wouldn't it be possible to do the same thing on a tiny Pico, like run all that Arduino code, or is that something that's not possible?
Don't know.
Because that, those are great little chips. They're like $10 and they're really powerful. But I certainly take your and David's point. Like that's why I got the Pi board. It's got an STM32 with plenty of horsepower on it. And it's got MicroPython built into it already. It's a great board and all the hardware's all there. So yeah, I'm trying to learn from David.
Well, this was my own failing because in the long ago, my robots were all HC11s. And then finally somebody convinced me to upgrade to a 68332. And so I fell in love with those only about 10 years too late. And then about 10 years after that, I was convinced to try the ARMs. And it's just everything I ever wanted in a robot controller, all there in one little tiny package. So they're currently my love at this point. But it's always possible that I'm again 10 years behind the time.
There's always something new, right? And that's what I figure is that right now I think I can make a lot of progress horizontally by adding stuff on to what I have. And then when it comes time to build the next one, I'll upgrade to MCU32 or ESP32, whatever it is. And then I'll add the Nixie tubes because you just have to have Nixie tubes on this.
I'm actually looking at Nixie tubes clocks right now, $300. They're beautiful. David, I think that I've actually come over to your side halfway, and that that running on an STM32 MicroPython, and this is a big if, is being able to port all the code that I've written in CPython over to MicroPython is really difficult. There's some real issues there, especially with the concurrent programming and the threading and stuff, or the pretend threading. If I can do that, then I would run the whole robot on the Pi board. And then the only reason for the Raspberry Pi would be Wi-Fi and having Linux kind of as the overseer. But the whole robot could theoretically run, apart from connectivity, would run on the Pi board. And if I can port my app to that, that's kind of my goal.
Well, you know what the Raspberry Pi gives you that you can't get from the Pi board is you get a TCP stack, you get secure shell, you get into the robot, you get camera, you get camera interfaces. And those are all valuable things that are real hard to do on a little robot controller.
Yeah, and that's
You
kind of
know,
the hybrid, is the having both actually is what I'm trying to work towards.
Well, and that's kind of what Chris has ended up doing too. Actually, he has, uh, I guess, slaves and masters. Is that the way you think of it?
On the IO side, yes, the slave and the master. I have my IO slaves, and the Pi is the master.
Yeah, I mean, I'm just a bit, as you probably all may remember, is that my biggest difficulty has always been how do you communicate between some kind of an MCU and the Pi, and I've never found a good way to do that.
You know, the guy in charge of this seismic program, who passed away a few years ago, used to say that all the money, all the expense, all the research, all the problems came down to comm and power.
At the end of the day,
Despite all of the money spent on all the other aspects, the parts that were constantly in need of attention were comm and power.
Because you guys may be aware of this thing. This is the Arduino Yun 2 Rev 2, and
You
this
showed
is
us.
a hybrid board that has an Arduino, a fully compatible Arduino, and then a second processor that runs an embedded Linux. And they both work really well. And this is a great little board. The problem is the connection between the two is imperfect at best. Even on a board that's integrated hardware, the connection between the two is a pipe that doesn't work very well.
They don't have a big chunk of shared memory.
No,
So
nothing like that. They have
Chairman, we're down a rabbit hole again.
it's called the Yun Rev 2, and it my camera's doing that thing, but basically there it is. But no, it uses some kind of a software pipe between the two of them, and so you can send things back and forth, but it's not very good. I was not impressed. I was planning to build a robot around that, but I'm not going to try. And the embedded Linux, which I forgot the kind of Linux it is fine, but it's not the Raspberry Pi OS with SSH and all that. No, it has SSH, but no camera, for example.
You know, there was somebody here in the group a few years ago, maybe Doug can remember who this was, that was using two miscellaneous processors to talk to each other. And the way they were set up, as I remember, was he was using an SPI to write a block of data between the two.
So can I suggest that we're down a rat hole?
Yep.
I have been called many things.
Rabbit hole.
I think it's
It's
so
my
easy
fault.
for us to get carried away. So I
It's my fault. I
apologize
take
for
the blame. Mea
opening the
culpa.
rabbit hole up and
We're
closed it.
3 hours in, and Pat has left, which is unfortunate because I have done an implementation of the proposed low encoder tick count that we've discussed. That actually I think Pat suggested, and I put up some code a couple of weeks ago, and just pushed more code, a new version of it that is now an Arduino library today, and it is working as I expected it would. I've had some feedback from Chris and Doug, and I'd like to show it, demo it, because I've now integrated it with the logic that can run the robot and see the encoder work while the robot's running. And it sort of works, seems like it's working reasonably. I don't have a ground truth, but I thought I'd just briefly mention that unfortunately I let the magic smoke out of my battery management system today when I got a new battery, so I went and replaced it, and I mounted all the wires nicely, and like adhered them to the walls of the housing, and did all the thing, made the wire lengths the right length, and did all the things that you do when you're doing a good job of it. But unfortunately, I don't have keying on the LiPo Sense connector to the BMS, and had it backwards on one of the batteries. So when I plugged in the main battery power, there was this and smoke emitted out of the BMS, and the one of the wires, one of the sense wires off the LiPo battery that used to be about this long. Well, the wire, the insulation was still this long, but there was only wire in about a half inch of it.
It's a good thing you weren't holding it at the time. I've
Do
burned
we
my
need
fingers that way.
Do we need to institute some sort of anti-prize for somebody who burns something up from the week?
A negative star.
Just
Purple heart.
Take a star away from him.
Gold
Or maybe
Band-Aid.
Yeah, I like that. The gold
maybe the
Band-Aid.
burnt match, you know?
Yeah, it was
No
really
star for you.
very sad. Very sad. This little black stubby wire is what was left of what used to be. It used to go with the rest of these wires to the sense connector. So anyway, that was my little tale of woe. But
I guess
We think of that
Could
as a
have been a lot
fusible link.
worse.
All those are polarizing connectors. They've got little, little ridges on one side of them, right?
yeah, but
Yeah, but you can force them together, you know.
I've got a loose wire. There's nothing to plug it into. There's no board-mounted jack to plug it into. I've just got like a set of 0.1 inch headers that I plug into that are wired off to the BMS.
You can get these. This is an accessory that came with my charger.
Yeah,
But-
I have one of them with my charger.
Yeah. So you have the.
Yeah. So anyway, that wasn't the main point. That was just in passing. But if we, let's see, I'm going to present. Let's present now. Present my screen. Oh. And hopefully you guys are seeing my camera.
Yep.
Okay, and I'm gonna switch over, and so here, and now you're seeing my code
Indeed.
window.
Yes.
So unfortunately, I've got a weird thing going on here, and that I don't understand. But you'll see some odd times pop up in like set drive motor request. Again, in set drive motor request. This is the time between when the task receives a message, knows it has a message, and sends it off to the robot and gets an ACK back. And most of the time it's 20-ish milliseconds. But every now and then I get values 150, sometimes even 300 milliseconds. So I'm not sure if this robot is actually going to be usable because of the occasional and not very occasional, actually relatively more often than I'd want, very long delays between issuing the command to the robot and sending it back and getting a response back. There's another one at 200. But anyway, what I'm going to do now is just shrink this a little bit. So that we can see the console and hopefully see the robot, which is running off of a bench supply because of the unfortunate happening with the battery. And so if I hit the 5 button in the code window, it tells it to go 50% of speed. And after a little while, so this algorithm, this loop is running through, turn the lights on flashing and the motor's off, then start the motors running at the requested speed, and then turn the lights back off again, turn the lights back on again, run the requested motors in the opposite direction at the requested speed. And you'll see in the code window where I'm actually getting speed out. And So if we look at, I'm also I've got a scope on the encoder output, and I'll just crank it up a little bit to. You can see some jitter, about maybe half a division's worth of jitter, and I'm on 5 milliseconds per division, so I'm seeing maybe a couple milliseconds worth of division of jitter, give or take.
Paul, are those quadrature signals we're looking at, or is that a left and a right signal?
It's a left and right signal. And I'm triggering off of the upper trace, obviously. So yeah, left and right. And if we look at what code is saying, and bring in to where we can actually read it a bit better. Let's blow this up. So we're seeing a speed of 0.27, 26, 26, 28, 30, 28 meters per second. And now I'll speed the speed up to 90% of full speed. It's still iterating through, hasn't picked up the last change yet. Okay, now we're running at about 0.50 to 0.54 meters per second. So anyway, this is just a demonstration that it actually seems to be working and giving approximately consistent results with variations in the 8% range, which is also consistent with about a half a division in about eight or so divisions on the scope. So I think it's actually working. And the operating principle of this is that it there are two magnets on the motor shaft. One makes the encoder transition high, the other makes it transition low. They're picked up by a Hall effect sensor. That the ESP32 is set up to interrupt on change. So both a high and low going change will trigger an interrupt. And at top speed, I get about one interrupt every 12 milliseconds. It reads the timestamp off of FreeRTOS that's running on the ESP32 in the Arduino environment and puts it in a queue. And then every 50 milliseconds, the odometry calculator task pulls out all of the timestamps that were put into the queue and counts the number of transitions, and that tells how far the wheels rotated, and uses the last transition to the next before last transition, uses that time delta as expressed in timestamps to compute the speed. So here's an example of where encoder pulses, there was a delta of 10 here, then the 50 millisecond frame time ended, and it computed the speed as something, whatever that 10 millisecond difference represents. Then we got several pulses happen during the next 50 milliseconds, and the most recent transition was at 140. The one before that was at 125. So that's a delta of 15 counts. So then after this frame time, the speed is reduced from one represented by 10 counts to one represented by 15 counts. During the next frame time, there's only one transition, but the previous transition happened 35 milliseconds beforehand, so it uses that to compute a new speed, which is lower still. During the next frame time, there are no transitions, so it sets the speed to 0. So this addresses the question that Pat asked of what to do when there are no transitions. You reset it to 0. In the next frame time, there's a transition at 260, so it uses the previous transition, which is at 175. So you got about 90 milliseconds between transitions, so it gives you a real low speed. So for better or for worse, that's the algorithm that I implemented. And so any questions on the algorithm so far?
Is this, you all, do you only have one channel and you have some other means of determining direction? Or do you really have two channels and you're just showing one of them?
There is only one channel per wheel, so it does not have quadrature. So I have to use the motor speed direction to tell what speed I believe it's traveling in.
So you have a separate signal to determine the direction.
Only what direction I've commanded the motor to go in.
Right. Okay. In other words, by what you asked it to do. Yeah.
Yes. Yes. There's no signal that tells me which direction it's actually going in.
I've implemented that before and it works just fine.
Okay.
Just using the control signal to tell you the sign, that works just fine.
Okay.
Paul, I have a question.
Yeah.
When you originally described it, I thought that each 50 milliseconds you read everything out of the queue and emptied it.
I do.
But now it looks like you have transitions happening inside one 50 millisecond window that are measured from those in another 50 millisecond window. So the queue can't have been emptied if you still have that, right?
No, that's not correct. I do empty the queue so that the queue is filled each time there's a transition by the ISR, and it's emptied on the 50 millisecond boundary. So on this boundary here, it will pull out 1, 2, 3, 4 transitions. So it knows that it's traveled 4 times 7 millimeters, because that's the distance that one transition represents. And it just uses the last 2 transitions to determine the speed. It's an open question as to whether I should be smarter than that and perhaps do some kind of averaging, which was something Chris suggested maybe I should do, to compute the average across these 2 transitions, then across these 2, then across these 2. I have not done that at this time, so I'm explaining how it works as of today.
I think I'm asking a simpler question. If you go to that transition labeled 260.
Yep.
Okay, so it's happening inside a 50 millisecond window.
Yep.
The previous 50 millisecond window is empty.
Correct.
And the one before that has a 175 in it.
Correct.
So that 175 was read out of the queue and is gone when the 260 happens. So
Correct.
how do you know to subtract 175 from 260 if the 175 is already gone from the queue?
Because I saved the last one away down in the odometry calculator task.
Ah, I see. I see.
So that's a great segue, David. If you're interested, I'll take a quick walk through the code and you'll see that working. So there's a queue. This is the queue that's used to put the timestamps in from the ISR level down to the task. You have to use this attribute in an ESP32 to get the encoder code to be in quickly accessed memory space. So that's what that IRAM adder means. So this is the function that's called when the left encoder interrupt detects a change, and it declares the encoder message, sets the wheel flag, gets the tick count from ISR. So this is a FreeRTOS call that returns the current number of milliseconds since the RTOS started, and then it puts that all in the encoder message. Then it sticks that encoder message into the queue, and so this copies the message into the queue, and that's it. That's the end of the interrupt. So it's real fast, non-blocking, and that's a timestamp. That's a timestamp in the queue. Same thing for the right encoder. Sorry.
Yeah, you said real fast in your email. You said 200 microseconds. I mean, that's actually not terribly fast. Did you turn optimizations on?
I haven't done anything. It's just like, yeah. So I was actually a little surprised that it took that long to put, because as you said in your email, Chris, this is probably the majority of it is in the send queue from ISR. So it's probably got to get a mutex, but I was kind of surprised it took that long. But other interesting thing, well, I'll talk a bit more about timing surprises later, but yeah, I was a little surprised it took 200 microseconds to do that, but that's what I measured. So then the init function, this is in the, so this is implemented as a library, as an Arduino library. So the way you do libraries in Platform IO for Arduino is within a project under the lib directory, you put the library name and then the source, and then you put the source code for the library files in there, and then you have a library.properties file that tells it, what the library is called and so forth. So anyway, this init just is called from the main from the setup routine, and it just sets the pin direction and attaches the interrupt. And then run is called from setup. Run is spawned as a task. So there's a method down in main.cpp called start run task, and it calls start run task, start odometry task. It calls mobot odometry, which is the object or the class that contains this encoder code, calls mobot odometry.run, and that calls this run method here, which then prints the running mobot odometry. And so it's then, and I'm sorry, I got distracted here. The start odometry task is actually spawned in a new thread, and that takes place in setup, where as part of encoder startup, it calls the setup, the Arduino setup function calls mobot odometry.init, which initializes the pins and connects the interrupts. Then if that returns okay, then it calls x task create, calling the start odometry task, which was that one we looked at just above here. So then start odometry task calls mobot odometry.run. So this is where the new task actually gets spawned. It's given a thread, a stack size of 2048, and an address of a task handle. If that succeeds, then it exits out of there, and then it goes on to run the loop task. So then run just does while true. So it runs forever. This task runs forever, and it here's where while there are messages in the queue, it reads out of the queue. Then it does the arithmetic about delta ticks and computes speed and so forth. Then it delays until the end of 50 milliseconds, and that's the code in a nutshell.
And so one thing I wasn't clear on, so per 50 millisecond time window here, how many encoded ticks are you getting? How many interrupts are you getting? I mean, I know it's very slow, that's why you're doing this, but what's the number per 50 milliseconds?
I've seen it as high as 7, or as low as 0 or 1.
Okay. 7 at full speed, you're getting 7 interrupts per 50 milliseconds.
Yeah.
Is that right? I thought the previous chart showed you were getting, 3,196 counts per 50 milliseconds.
So
That's a
for example,
cumulative count, it sounds like. It's a cumulative, right?
yeah, this is the cumulative encoder count. So this is the odometer. And so here we are running at 0.58, which is like nearly full speed. It's 90% of full speed. And if you look at the count differences, there's 8, there's 7, there's 7, there's 8. So yeah, about 8 counts, 8 interrupts per 50 I'm sorry, 8 milliseconds per encoder tick. Per encoder count, I guess you'd call it. Per encoder transition.
So that works out to about 7 transitions per 50 milliseconds.
Correct.
So if you didn't do this, right, then your granularity of speed measurement would be, well, it's either 0, somewhere between 0 and 7, right? You literally would have only a resolution of 3 bits in a way, right, of
Yes.
speed measurement, because you'd have either 0 ticks per time interval, or you'd have 7 ticks.
Yes.
Ticks per time interval. I mean, that's just a little
Right.
over 3 bits.
Right. And this part of the console log shows running at 50% speed. I know that because the speed is about 0.28, 0.26. And here you see we have 3 counts, 4 counts, 3 counts, 4 counts, 4 counts, 3 counts. So yeah, at half speed, I'd only have 3 counts per 50 millisecond control loop period. So this is why it's advantageous to use timing between encoder transitions on this robot versus number of encoder transitions.
The question then is, though, you time stamping with the resolution of 1 millisecond, right? Is that giving you enough timestamp resolution, right? So, what do you need? Do you need something more accurate?
Yeah, it's a good question, Chris, and I appreciate you bringing that up. And I think it's kind of on the edge, because the at 8 counts per 50 milliseconds, I'm getting a count every 6 or 7 milliseconds, and my timestamp readout resolution is 1 millisecond. So that's about a 15% inaccuracy right there, due to using milliseconds as opposed to microseconds. So I could get better accuracy by using microseconds.
Did you say 80 counts per
50.
what time interval?
8 counts in 50 milliseconds.
Eight. Okay, I misheard that. Okay, eight counts per 50 milliseconds. Right, that's top speed. Yeah, so that's yeah.
Even then, though, that means you would have a maximum possible speed of 25 ticks, right? One millisecond to go positive and 1 millisecond to go negative. So in a 50 millisecond window, it's Nyquist frequency, right? It's a 50 millisecond sample rate at 1 millisecond means the maximum speed would be 25 counts, but you're nowhere near that.
Correct.
I'm real interested to see if this works. It looks like it is. It looks like it is working.
But wait a second. I mean, maybe I'm not following something. It seems like you could use both bits of information. You could use the number of encoder transitions in a 50 millisecond window, and then you could also use the delta number of clock ticks, which in this case is 1 millisecond.
I am using both.
You are using both. So you could have like 100 encoder transitions in a 50 millisecond window.
No.
No.
The encoder transitions twice each motor revolution, which is a maximum rate of 8 times in 50 milliseconds. So 160 times a second.
For this motor then?
For this motor.
Okay, but the algorithm, if the motor spun faster, you would have number of ticks plus time delta, right, in general?
So he would be using one or the other, right? Then the number of ticks he's still going to use for odometry, for actual, keeping track of X, Y, and heading. But for speed, are you suggesting, Carl, to kind of somehow merge the two pieces of information together?
Well, yeah, it sounds like if you really wanted precision, you got these encoder ticks that could measure. I mean, when the motor's turning slowly, the encoder ticks are a coarse measure, and the time delta then gives you additional resolution. But when the encoder's spinning, when the wheel's spinning really quickly, then you have a lot of encoder ticks.
But he doesn't have a lot, right? That's the thing. At full speed, he gets
right.
At full speed, he gets like, let's just say 10 encoder ticks per 50 millisecond interval, right? It's really that slow.
Yeah, I think Carl was talking about generalizing the algorithm for a motor that could go faster.
Exactly. Yeah. Because
Paul, this is essentially your sensor is actually on your wheel shaft, isn't it?
Yeah.
Or somewhere down the train.
Well, the sensor is on the actual motor shaft.
On the output?
The output of the motor.
Okay, output of the motor. Okay, because what I'm saying is, I'm sure the motor's turning a lot quicker. It's being geared down, and that's why you get so few ticks.
No. It is actually turning that slowly. It is actually only turning at 80 revolutions per second at full speed.
Yeah, but it's a gearhead motor, and you're on the output shaft.
Oh yeah, I don't know whether it's got internal gears or not.
It's got to have to. I can't imagine. I mean, the thing would be burning up the brushes and being so hot. I don't see it. You're only turning. I mean, just in my opinion, I imagine the motor's turning really quick, and then you've got some output gearing somewhere and you're measuring down the output. This is the classic, where do you put your encoder? Do you put it on the end of the motor shaft, or do you put it on the output? You always want to put it on the motor shaft because it's not geared down.
Paul, can you see the motor shaft where it comes out the other end? Can you see it with your eyes?
No, there's a back plate over it.
I was just curious if looking at it showed it turning at the same speed as the output shaft or turning faster than.
Yeah, it's a really good question. I don't know.
You know, if it's turning faster than the output shaft and you can get to it, that might be a nice place to put an encoder.
Right. I know I can't get to it unless I disassemble the motor, and then I'm not sure what I'd find. You know, it's a round, looks like a beefy motor, about 2.5 inches diameter and about 4 inches long.
Well,
And
you know, the coreless motors can turn that slow. They can be designed to turn that slow with a lot of torque. But if it's a standard brush DC motor, they don't have any torque down there. They have to run fast.
Oh, okay. So there must be a gear head in the front of the motor, perhaps.
Mhm.
Interesting. Back to Carl's point, because I hadn't really caught what he was suggesting. That you said he was suggesting, David, that he was suggesting generalizing this to motors that can run over a wider range, or really to enable running a motor with control over a wider range, to where you would use number of pulses at higher speeds and period between pulses at lower speeds. That's sort of interesting.
Well, if I could expound on that, thinking further, and David's mirror feedback helped a little bit. It strikes me that, and I noticed this earlier too, that when I look at this diagram, it strikes me that your approach, Paul, is almost, you can view it as one of synchronizing asynchronous spaces. So the challenge is that the encoder pulses and transitions are happening at pretty close to the same frequency as the sample periods of 50 milliseconds, but they're asynchronous. So in a way of thinking, one way of thinking I have in my brain is that this algorithm that you have is a way of you're capturing the incoming encoder ticks on the one side of the synchronizer, and then on the other side you're taking that information and you're bringing this asynchronous encoder tick information into synchronous 50 millisecond space.
Yes.
And so then I take this thought a little bit further, and I think that, okay, let's say that the motor is turning really, really slow. So there's you're having like numbers of 50 millisecond periods between each encoder transition. Well, now you have the case where you're just counting clock ticks between transitions. And at the other extreme, you have like David's robots, where he has a gazillion encoder ticks per like every millisecond. You got so many encoder ticks that, so at the end of the day, you're throwing a bit of information out, right? You're either throwing away a fraction of an encoder tick, or you're throwing away a fraction of a 50 millisecond sample period. But what struck me about your approach here is that you're actually capturing both bits of information in the way that you synchronize them. So you're capturing the time between encoder ticks, but you're also capturing the delta from the last encoder tick to the current sample period. So it's like you have a way of somehow, it seems like you're able to get even more resolution than either one alone could provide. Maybe I'm just rambling now, but it's interesting to me.
It's sort of like extending the low end.
Yeah.
There was a robot builder out in Seattle named Larry Borello. Some of you may know that name. Larry went off to professional robotics and we lost him. But he had a robot that worked the same way. He measured the distance between encoder ticks. And one of the cool things he could do is he could make that robot move, a foot per hour at a steady rate. It was actually quite astounding to watch because he had that low end available.
Huh.
So I have seen that work. Yes.
Huh. Interesting. So anyway, I think that's the majority of what I had. I don't know if you guys are interested or Well, it's getting late. We've been going for three and a half hours, so maybe it's time to wind it up.
4 hours. Oh no, 3.5.
Or if it's something interesting.
It's almost Wednesday on my end, so yeah.
Well, great job, Paul.
Pretty cool.
Thank you. Thank you for the presentation.
That diagram helped a lot.
Black star, black star.
Absolutely.
One nuclear bomb, right?
Yeah.
Black star and a nuclear bomb.
Yeah.
Smoky star.
One lipo frying event.
Carl, I did have one.
What's that on this black star thing? What's like that's actually when you get kicked in the ass or something like that? What's
No,
that?
no. Black star means you've made significant progress.
But you didn't put a robot on the floor and
run it.
So that was a gold star. The reason it's black is because that's the only color Doug could make work.
Yeah.
Carl, I have one more comment for Chris that I jotted down when you were describing your arbiter, and you said you weren't certain what to do when nobody had a command, and that's basically in a standard subsumption engine. That's what the default command does. It's always true. So, and it may be put the robot at a stop or drive in a straight line or whatever. But that's basically how that problem is solved, is that you never fall through the loop without finding something that's ready to go.
Right. Like the idle task. Yep, got it.
Hey, just a dumb question now, because we've had a few meetings that are like 2.5 or 3 hours, and we've had some that are 3.5 and 4 hours. So, what's the right length actually to aim for?
Well, my butt starts to get numb at about like 10:15. So I think
45 minutes ago.
Yeah,
I think we go until we're out of
steam.
Until we're so far down the rabbit hole that somebody calls fault.
Yeah, because I think people make uneven progress. Like last week was everybody came together and made fantastic. And today, it was a good one too. I mean, we had, I'm giving out 3 black stars, but sometimes I haven't given out a star. I bet those are the shorter meetings. So, I mean, I wouldn't want to discourage anybody from getting their chance to share their progress.
Well, I'll have one other little tiny thing. If everybody will give another 2 minutes here, I can get it done. Murray.
Yeah.
Murray, how's your wife?
Metastasized.
Sorry to hear that.
Yeah, she's actually back in Japan and started radiation therapy this week. So,
Will you tell her that there's an entire group of international roboticists that are pulling for her?
I will do that. She's doing all right. She's doing as well as can be expected. She looks good, and she's keeping her heart together, and living with her mom.
That's tough stuff.
Living with her mom, yeah.
Oh. Well, so can I present here for a moment?
Yeah.
And then I'll get out.
Jump right in.
Print my entire select screen on window. Screen. Did that do anything?
Yep.
You're presenting.
Okay. We talked about this last week. I just wanted to clear this up. Chris had mentioned that he was still he was confused about how the calculation of the rotation of the robot was clipped. And I had mentioned at one time that I used 2 different calculations of theta, one called total theta, which is not clipped. But that's not how the odometry is calculated. So if you look at this line right here, this is what I described before as being like a floating point function, like a modulo function for floating point. And it does exactly the same thing that your 2 if statements do, except that you don't have to keep track of the sign and no conditionals are involved. So basically, you're going to take theta and divide it by 2 pi and take the integer of that. So in your case, that'll return a 1. And then you multiply that times 2 pi and subtract that off of theta. So let's say your current theta was 370 degrees. So 370 divided by 2 pi, an integer is 1, times 2 pi is 360. So that's theta minus 360. So it automatically keeps track of the sign for you, since the sign is in theta to begin with. And as I say, you don't need to use the conditionals. But other than that, it does the same thing.
Cool.
So that's it.
Thank you.
Nice.
How do I unpresent? Stop presenting.
Just like that. Cool. Well, 3.5 whatever hours. Any other last minute things for this week? And it sounds like we have a move to adjourn, guys. It's been fun. Don't freeze in Dallas or wherever you happen to be. And we'll see you all next Tuesday.
Great presentations, everybody.
Keep off the
Thank
street.
you.
Yeah, thanks, everyone.
Fun
Take
night.
care.
Thanks.
Bye.